One, two, three. Okay.
USB-C thing out there, right? This thing.
Let me. Cool. I try. Rok, can you say that we are online? So good morning, everyone. Welcome to the fourth Stanford Graph Learning Workshop. My name is Yuri Leskovec. I'm the organizer of this workshop. This is the fourth workshop we've been organizing, so it has quite some tradition. Before I go and give a few opening remarks, I would just like to say that the event is also live streamed at the link posted below, so feel free to post and share that link over social media and with your own organizations. And then we also have a Slack community and a channel in the Slack community where you can join and keep the discussion going. And the Slack community is, you can subscribe by going to data.pyg slack.html. So that's where you go to subscribe to Slack, and then there is a channel called Workshop 2024 to keep the discussions going. So welcome again. So the topic of today's workshop are several. First, we are going to talk a lot about how do we learn over complex data. And when we talk about complex data, we mean data that goes beyond a fixed size matrix or that goes beyond a linear sequence. And when we start thinking about this type of complex data, naturally graph as a representation of entities being connected as nodes comes into play. So graphs represent objects and their relationships as nodes and edges. And these graphs, right, can be richly labeled, can have different node types, can have different relationship types, and so on. So it is no wonder that we see this kind of graph modeling in many, many different domains, beyond, let's say, social network analysis. We see a lot of this in modeling knowledge graph, and triplets of objects, be it in healthcare, biomedicine, or somewhere else. We see graph-based approaches to be extremely important when we talk about learning from human behaviors and traces of human activity, meaning about customer behavior in commerce and retail. When we talk about detecting fraud, anti-money laundering, and things like that in financial industry, those are inherently graph problems. We also see graph problems when we think about transportation, supply chains, finance, in insurance, as well as in manufacturing. So today we are going to see applications from many different walks, many different industries. The second important topic that we are going to discuss today will be around foundation models, especially how do we bring in structured data into large foundation models, how do we bring in structured data in large language models to prevent hallucination, increase accuracy, be able to bring in real-time specific knowledge that LLMs have not been trained on or have not been fine-tuned on. So that will be our second big theme for today. So what we are going to discuss is recent methodological advances in AI, graph machine learning, foundation models, and multimodal AI, how these technologies propel a wide range of applications in a wide range of industries, and we are also going to talk about tools that we can use and platforms that we can use to make all this happen. We have put together a very exciting program of invited talks, as well as a poster session that will happen in the afternoon from 4 p.m. onwards. We have a set of talks from leading Stanford researchers, PhD students, postdocs, as well as talks from industry, 2 coffee breaks, and a lunch in between. And then the poster session will have a poster slam, which is a 1-minute presentations of every poster. We have a set of internal Stanford posters as well as external poster presentations. So the afternoon will be kind of devoted to discussion, talking, and going more in depth. In terms of the overview of the program, we are first going to focus on methodological advances around improvements in the PyG library and other open source toolkits for graph learning. We're going to talk about graph transformers. Then the morning session will actually be focused on learning over structured, semi-structured data, right? Thinking about the data that is stored in our data warehouses in a form of tables interlinked with primary foreign key relations, how that data can be represented as a graph, and how now predictive modeling over a database, which is basically what 90% of the data scientists are doing daily, can now be represented as learning predictive models over graphs. And the exciting thing here is that if you represent a database as a graph and let a graph neural network learn over this representation, we don't need to do any manual feature engineering. We are going to talk in the morning about approaches in this domain, as well as the open source benchmarks and toolkits to make this happen. So that's kind of the morning session. The session before lunch is going to focus a lot around combining graphs and LLMs to train more accurate LLMs that are better at reasoning, as well as thinking about knowledge graphs and how do we bring structured data, semi-structured data, as part of the RAG process into the LLM reasoning pipeline. So this is what's going to happen kind of before lunch. After lunch, we are going to continue this theme of LLMs, and we are going to talk about research agents. So there will be a session devoted to agents, agentic workflows, and how do we enable closed-loop systems, especially in science and discovery. And then the afternoon session will be about different applications of graph learning across many different domains. We are going to hear from Amazon, NVIDIA, and Hitachi, as well as Kumo.ai, about the latest advancements and applications of graph learning technologies to their industries. And we are also going to talk about applications in healthcare, biomedicine, and drug discovery. So this is a quick overview of the program. And then at 4 p.m., all the speakers during the day are going to present posters, as well as a number of external people, 17 of them that we were able to accommodate. We had many more submissions, I think over 80 in total, but we were only able to accommodate 17 external poster presentations. And that's going to happen outside in kind of sunny California weather, as we are all used to. So with that, would just like to thank the organizing team who helped make this event possible. So thank you, Harilaos, Keshin, Rok, and Lata for organizing the program and helping with that. And then also thank you, Joseph and his team, Sarah, Nancy, Jason, Oksana, and Malwana, to create this beautiful atmosphere and take care of all the logistics and delicious food and live streaming and so on. So thank you so much, and I'm looking forward to a great program. So the first speaker for today is going to be Josh Robinson. Josh, do you want to come up here? So Josh was a postdoc at Stanford and recently started as a research scientist at Isomorphic Labs. So this is the DeepMind spin-off doing drug discovery. And he'll talk about graph machine learning, relational deep learning, and then we'll follow by other talks.
Cool, great. All right, thanks, Yuri, for the introduction. And it's really nice to kick off the day here. So yeah, as Yuri said, I'm a recent alumni from the lab, but I'm going to talk today about some of the recent efforts that have been going on in the lab about doing deep learning on relational databases. So this has actually been a big focus in the lab recently. And so there's going to be essentially 3 talks back-to-back that are relevant to this, of which mine will be the first. And so my goal will be to present essentially the kind of the proposal, the blueprint of what we're doing here. And then I will hand over to Matthias and Aki, who will talk generally about recent developments in PyTorch Geometric, the new popular graph machine learning library. And that will include certain developments that have been made with our relational deep learning project in mind. And then after that, it will be Rishab coming, and he will show essentially kind of the work we've been doing to develop what you could call like the research infrastructure necessary to explore this space. So everything from like benchmarks, user studies, and kind of empirical validation. So in terms of results and stuff, that will come later in Rishab's talk, and I will not be doing that. So the story starts with the really simple observation that the relational databases are really one of the major sources of data in the world, and they span essentially all types of human activity and pursuits. So everything from online commerce, social networks, medical, electronic healthcare records, and so on. And all of these different types of data can be stored in these sets of different tables of information that are linked via IDs that can cross-reference across these tables. So in the case of the e-commerce, you have tables of users and information about them, tables of products, information about them, sales, and so on, and these are linked via these IDs. And so because there's so much of this data just out there in the world, there's all manner of different machine learning tasks people are solving over this data every single day. And so in the case of the e-commerce, this could be things like things that inform business decision making. So predicting customer churn, value of customers, and so on, so you can know who to prioritize, predicting affinity between users and products, and so on, and then things like fraud detection as well. In the case of the electronic healthcare records, this could be other kinds of decision-making problems, such as trying to anticipate the risk that a patient, if they were to be discharged, may have to return to hospital, which would be a personal medical risk to them, and then also a logistical challenge for the healthcare network. And also other kinds of things to anticipate, such as if there is any patients that are a short-term extreme risk. And so all these are examples of a predictive kind of machine learning tasks as opposed to generative, and these have sort of lie in slightly different, have slightly different use cases. And so this morning we'll be focusing mostly on the kind of predictive side, and then as Yuri mentioned, there'll be more generative later. But broadly speaking, the kind of use cases we have in mind for predictive are things like personalization, decision-making, informing decision-making, things like that, and these have a kind of, you could say like a strength for being applied to privately held relational databases. Okay. So although there's all sorts of databases and tasks and so on out there, the fact remains that actually the model development cycle on these databases is very slow and manual. And so to explain kind of on what I mean by that, I'll give a brief sketch of the high-level ML considerations when doing this. And so let's use the running example of this e-commerce data set and predicting churn on that. So the first kind of very simple observation to make is that this data is very irregular in structure and heterogeneous. And so it's not easy actually to feed this directly into a machine learning model that can just ingest the data in exactly the format it's found in. And so a standard initial step would be to transform the data into a more amenable format for machine learning models. And so in particular, a very common step would be to produce a single table of data that can then be fed into your model. And this table is built in a kind of manual way by using query languages like SQL to produce column features that you think will be predictive for the task. So in the case of churn, it could be things like number of purchases a user makes or the time since their last purchase, most common price point, and so on. And then once you've got that table, you would then feed that into your tabular machine learning method, like XGBoost or whatever other tree-based method you like. And then that will produce the model that you deploy. But an important point here is that the machine learning model that you're using, the tabular model, is essentially bottlenecked by whatever predictive signal is left over in this table that you've produced. So the table will only be a partial snapshot of the full predictive signal of the database. And so the best that the tabular model can do is whatever signal is left over after the kind of manual construction process of this table. And so for that reason, you would sometimes have a kind of iterative process where you may go back and you would update again your table. You would get new features that you think may, based on the first model, may further improve your model. And so this kind of manual process is really obviously in sharp contrast to the situation across a lot of other domains of machine learning, so vision, language, so on, which at one point were in the same kind of situation of crafting, handcrafting features, like in vision, SIFT features used to be big, other kinds of object edge detection features and so on, which then be fed into a generic model, such as an SVM or something. And so the whole kind of story of the last 10 or 20 years, as everyone knows, is you replace all of this with a big end-to-end model that is able to operate directly on the raw perceptual pixel level features of your data. And so this kind of begs the very obvious natural question, which is how could you do a kind of end-to-end deep learning style of problem solving for relational data in exactly the natural format you find it in? And that's essentially the question that this line of work that's been developed in the lab at Stanford has been aiming to address. And so the approach that we have been working on is something we're calling relational deep learning. And I'm going to go through the the idea behind this next. So as Yuri mentioned, and actually I think if there's just a single slide that you remember from like my talk and what Yuri was mentioning earlier as well, that you remember, I would like it to be this one, which is the fundamental idea is that you can view the database as one big graph and then process that graph with your machine learning models. And so the way you can build that graph given a database is to say, okay, every single row and every single table will be a node. And then you connect up those nodes with edges according to the foreign key, primary key links in your data. So with this example here, you have users, products, and sales tables. And each sale will reference the corresponding user and product involved in the transaction. And so you would simply connect that that sales node to the corresponding user and product nodes. And so when you do that, you now have a graph with nodes, and then they're connected up with edges, and you would finally add features to this graph by taking whatever kind of column information is in your database and adding them as features to all the nodes. So in the case of the user, okay, there's no, the schema at the top is kind of illustrative, so there's no columns shown there, but you could imagine the sort of thing might be like when they joined the service or whatever, and that would be added as a feature to the user nodes. Likewise, products could have categories, they can have text descriptions of the product, they could have images of the product. All this potentially multimodal features will be added as node features to those product nodes. And so the important point here is not just that you can transform the database into a graph, but actually this is essentially an exact or lossless description of your database. Another way of putting that is that the map is invertible. You can go from database to graph representation and then back again. So you've lost absolutely nothing, and all the same predictive signal that's present in the database is still there in the graph. And so any model that's able to ingest and process the whole of the graph has available to it for making predictions everything in the original database. And so with this graph view, all the predictive tasks we're talking about just become different kinds of graph machine learning tasks. So the churn and lifetime value are just node level tasks on the user nodes. The predicting affinity between users and products is now a prediction on pairs of nodes, which we'll call a link prediction task, a link level task. And then fraud detection and things like that would be predictions on groups of nodes, which would be like subgraph level or graph level tasks. And so I know this is a graph machine learning workshop, but I'm going to just do a 10-second aside on GNNs, which would be relevant to other talks later today as well. So just to make sure 100% of people are brought with us. The model that we'd apply on top of this graph would be something like a GNN. And the basic way that this works is that it will embed each node in the graph as some embedding vector from which you can read out different predictions from in the same way as you use embeddings in any other area of deep learning. And the way that these embeddings are obtained is through this kind of iterative information pooling across neighbors. So for example, if you have some target node A, it has already some node features that you initialize with, and you would update those features by feeding through some learnable model the features of its neighbors to produce a new updated neighbor-aware representation which you add to that. And then you can do that in parallel for every node in the graph at the same time, and you'd repeat this process iteratively so you get receptive fields that grow across the graph, and each node is able to communicate with others that are far apart. And so with the GNN model applied on top of this graph representation, the other thing you would need is a way to actually supervise these models' training. And in this case, we're fortunate because essentially that supervision can be mined directly from the database without requiring human manual annotation. So for example, if you're predicting the value of a customer in the next 90 days, then you can simply roll back the state of your database to 90 days in the past. Let that be your point in time of prediction during training, and then use the intervening time interval to compute ground truth data. And so in a certain sense, this is kind of like a self-supervised training approach in the sense that you are not manually annotating this data. You can compute ground truth supervision from the data as you find it. And so overall, the new pipeline that we are looking at that's replacing this kind of SQL table-based, single table-based approach will be to take the database, transform it into this exact graph representation, and then use an end-to-end GNN model on top of that, which would be the model you would then serve into production. And so the last thing I want to talk about now before I wrap up is just to go through and emphasize some of the key advantages that we anticipate in these relational deep learning approach. So the first advantage, I think, is very obvious, but I just want to spell it out, is that ultimately we do expect much more accurate models from this. And the fundamental reason for that is that the model that you're using is now fully end-to-end learnable. And so it's able to actually learn features that are task-dependent in a more optimal way than if you're using kind of SQL-based feature design. And in a sense, the GNN is doing something quite similar to SQL in that it's pooling information across tables in the same way that SQL is something that you can use to aggregate cross-table information. But the GNN is doing this in this kind of message passing style learnable way. Following up on that, adding on top of that, okay. We also expect the GNN to be capable of a kind of multi-hop kind of reasoning, or like ability to learn more complex features. Because the GNN is able to pool in this iterative way across many neighborhood steps in the graph, it's able to take into account relations between larger groups of nodes and more like higher order kind of relations in its representations and the downstream predictions, which is something that's quite hard to do with in a kind of SQL type of approach where you are sort of constrained by the complexity of the queries that you can even conceptualize. And so we expect there to be some sort of headroom in terms of like extra predictive signal that the model is able to utilize here. Another advantage is a kind of temporal correctness. And so what I mean by this is that the GNN can be applied at any different point in time in a relatively simple way. Because whatever time point you would like to make a prediction, you can, inside the model, you can constrain the information that is allowed to flow by saying that the target node in question at whatever arbitrary time t is only allowed to receive messages or information from neighbors that have timestamps in the past. And so in this way, your model, essentially nothing needs to change if you want to apply it at some new time point in the future. If you put this into production, you just apply the exact same model to the new state of your database. And this is in contrast to building single tables, because the single table is inherently static. And so if you want to reapply the same model later on in production, you would have to do this kind of feature recomputation step. And you'd have to manage the different sets of features at different time points and so on. And then lastly, a kind of upshot of all this is that ultimately you do expect there to be a lot less manual work because you're not having to manually engineer the features your model is using. Okay, and so actually with that I will end, and I will just thank the people that were involved in this project and also the subsequent talks and so on that are up here. And I would just highlight a couple of things. We have a paper at this year's ICML that fleshes out like a more full version of this vision. So if you're interested, you should check that out. And we will also, of course, have a poster at the poster session later if anyone wants to stop by, say hi, and chat at that point as well. Cool, thanks.
Thank you, Josh. Do we have any questions? We have time maybe for one question. Yeah, go ahead. And then Aki, can you come and prepare?
Hello. Hello. Yeah. Hi. So you say that the major contribution is that you don't need feature engineering anymore, but how do you make sure that there is not some data which correlates with the target, but is not actually causing it, or it's not useful?
Like, how do you, I mean, I feel like that's a very kind of generic issue of disentangling correlations.
But during feature engineering, if you have some domain knowledge, you could probably leave those things out because you just, I mean, when I look at an enterprise SQL ER diagram, there are too many tables which are not actually storing. I mean, there could be ordered tables and other stuff like that, which I know is not related to the target, and I could just leave them as part of my feature engineering. How would I go about that here?
I mean, on the table level, you can, if you have that prior knowledge, you can leave out certain tables from the graph construction. So if you would like to add that kind of prior knowledge, you can do it in a similar way prior to graph construction.
Maybe I can answer your question. So actually, there is a benefit to what you said, is because these models can be just learned over your data. So you can essentially ask them, what data are you looking at, right? So if it's looking at columns that it shouldn't be looking at, you as a data scientist know, you can simply remove those columns from the data or remove those tables from the data. So it actually allows you to discover this kind of information leakage type situations much faster, because you don't spend time to putting it in and so on. You just see whether the network kind of latches to that information, and then you decide, do I want it to learn from this or not? So it allows you to iterate faster and discover these bugs faster.
That's true. And we found that also we've done exactly that in some of our experimentation to identify time leakage.
Awesome. Thank you so much.
Cool. Yeah, thanks. Oh, I see.
Okay. Super. So the next speaker is Akihira, or Aki Nita. He's a core contributor to the PyG open source project, which is the most popular library for graph machine learning. Aki is also a machine learning engineer at Kumo.ai. Aki, the floor is yours.
Hello. Thank you for your introduction. I'm a software engineer at Kumo.ai, and I'm a contributor to PyG. And today I'd like to sorry. It's not. Okay. Okay. Sorry about the delay. Today I'll be presenting on relational deep learning in PyG. And as well as other projects that we were working on in the ecosystem. This presentation will also cover recent improvements in these libraries over the past year. To begin, let's quickly go over PyG and its community projects. As you might already know PyG is a graph neural networks library that brings together the state-of-the-art graph representation learning. It includes everything you need, basically, to work with graphs in PyTorch, from model components, data sets, data loaders, and so on. And the second project that we released end of last year is PyTorch Frame. PyTorch Frame is a tabular deep learning framework which is focused on which bundles state-of-the-art components, data sets, and optimal sparse data structures for tabular data, and to make deep learning on tabular data more accessible and performant. And the third project is RelBench, is a relational deep learning library that provides end-to-end framework for learning on temporal, heterogeneous, and multimodal relational data. And before diving deeper into the later talk, I'd like to thank our community on all the support and contributions you make. And PyG has now have 22K GitHub stars and now over 550 contributors on GitHub, so thank you. And so now that we quickly went through the projects we're working on in the ecosystem, I'd like to introduce some of the recent features and improvements that we've added to the PyG ecosystem. And the first one is compilation. As part of PyG 2.4 and 2.5 releases, we improved torsional compile integration in PyG. Previously, users had to use torch-geometric.compile, but with native support for torch.compile, we fully moved away from torch-geometric.compile. We also addressed graph breaks from PyG model components to enable faster model execution, leading to 3x faster compared to eager mode in PyTorch. And another exciting feature to highlight is distributed training. In PyG 2.5, we added a new sub-package, torch-geometric.distributed with Intel to enable distributed training in PyG natively. This shows only one way of distributed training, but how it works is that it first partitions a larger scale graph into multiple partitions, and then we place each partition onto each node, compute node. And each machine samples subgraphs based on local nodes from its partition, as well as halo nodes from partitions on other machines. And another feature I'd like to highlight is we added edge index tensor as a dedicated graph tensor representation in PyG. Previously in PyG, there were different graph tensor representations, and it was confusing a lot of users. But now with the newest PyG, it unifies all these different concepts by representing a graph as a PyTorch tensor subclass called edge index. As you can see on the right-hand side, it's just a PyTorch tensor with metadata, and it allows, it optimizes PyG workflows in a few ways. For example, CSR from COO to CSR and CSC conversions are only computed once instead of computing them every GNN layers. And also, knowledge of undirect graphs avoids transpose and backward pass. And another another thing to highlight, which Rishi will be talking later this workshop, we added LLM support to PyG. We added torchgeometric.nn.nlp for fast access to LLMs, and also an example of GRetriever available in the repository. And we are currently running a community sprint, and so feel free to join our Slack and contribute. That would be great. And another one, the most, I'd say, recent feature is cuGraph loaders by NVIDIA. It basically samples on GPU instead of on CPU, which is the native implementation on PyG. The sampling speed is 6 times faster than the CPU one. And also, it's seamlessly integrated into PyG so that you won't see any friction in interface. And also, we are adding single node and multi-node examples that use cuGraph loaders very soon. And as part of 2.5 release, we added full support for REXs, recommender systems, in PyG, which means that previously in PyG, link prediction models were evaluated using using binary classification metrics, which is impractical since it requires candidate generation in advance to evaluate on. However, we also wanted to find the top k most likely links from the full set of pairs. For example, in this case, source node embeddings might be user nodes embeddings, and destination node embeddings might be product node embeddings. And with REX's support, you can do all these things in PyG. And as you can see on the right-hand side, code is relatively simple. The first for loop will create an index of destination embeddings, for example, product embeddings, and then in the second for loop, you will compute the embeddings for users, and then using that embeddings, we want to search top k recommendations from using the index. And we also added retrieval metrics, subclassing torch metrics, which allow us to compute the metrics in each mini batch iteration without having to accumulate all the values during training. And this is exactly what we do at Kumo, and we successfully applied this scheme in Kumo to perform recommendations over 200 million users across 10 million products. And another one of the PyTorch PyTorch Frame is one of the projects that we've introduced recently. It's a modular framework for multimodal tabular deep learning. PyTorch Frame enables deep learning on multimodal tabular data, and it was deep learning on multimodal tabular data where you have different types of columns, such as text, image, or categorical, multi-categorical, or text, and so on. And PyTorch Frame provides PyTorch tensor-based data structure so that you can apply all the PyTorch operations to it without having to be locked in some frameworks. And it also provides three-stage plug-and-play model interface And these column types are what we support so far. And we also support native integration with foundation models. The previous talk introduced relational deep learning concept. So now I'd like to focus a bit on how to implement it in PyG. And with PyTorch Frame and PyG, implementing relational deep learning becomes very easy. At a high level, as you can see on the right side of the slide, we first embed each table into a table representation using PyTorch Frame, and use these table representations as node features to pass to GNNs, to PyG, to exchange messages between across tables. And this has been made possible thanks to PyG's support for TensorFrame from PyTorch Frame in data loading schemes, as well as data and hetero data objects in PyG. And so now if we have a closer look at data loading, what we want to do is for a given training table example, user ID, seed time, and target, we want to query the historical subgraph around the user at seed time. And so, as you can see on the bottom of the slide, it's extremely easy to do that with PyG. PyG supports temporal sampling, and so you don't have to think about taking care of. Well, PyG ensures that no future links will be included in your batch. And PyG, and now if we look at the model definition, we will see that we can build a model using built-in PyTorch Frame and PyG model components, such as you can see in the code snippet, tab transformer is one model for customers table, and we use trumped model for products table, and also as a GNN, we use GraphSage and converted it to heterogeneous network so that it works on different node types. In this case, customers node type and products node type. And within the forward pass, it's also very simple. We first encode table features individually per table using PyTorch Frame, and then we fed that xdict, it's node features, and we feed that to GNN to exchange messages between across tables. And for example, on the bottom right, as you can see in the bottom right figure, the prediction is based on customers feature, which also depends on transaction stable, and then transaction stable also extracts information from product stable. So by doing relation deep learning, you can extract a lot of information from different places to make prediction for each user. And now we had a look at model definition, so it's time to train the model. And as we already made a loader and model, this code looks pretty looks like a pretty normal PyTorch script where you pass input into model and to get predictions, and then we compare predictions with the target labels, and then do the backward to compute the gradients, and then update parameters. And in this case, parameters mean that the entire model parameters from both PyTorch frame and also PyTorch geometric. And so we at Kumo and PyG keep investing in open source. We've covered, in this talk, we covered recommender systems, multimodal inputs through PyTorch frame, and also how to implement relational deep learning using PyG and PyTorch frame. And then we also investing into LLMs integrations. And also we covered the new edge index tensor subclass. And yeah, as a future work, we are looking into trainer integration for improved efficiency and fused operations. Triton, for those who don't know, who are not familiar with Triton, it's kind of a higher level CUDA. It's Python-like GPU programming language, DSL. And then we want to have some sort of custom kernels to speed up training or inference and so on. And although we deprecated all the sparse metrics data structures, we still have to make an edge index the single source of truth across all PyG and we're also running GNN plus LLM community sprint, so feel free to reach out to us and advance relational deep learning to new use cases and applications. Yes, and that is all. Thank you for listening.
Thank you very much, Aki. Any question? Yeah, please go ahead.
Can you explain the 6x speed up from moving sampling CPU to GPU? What is the source of that speed?
Good question. I don't have good visibility, but generally speaking, CPU is a latency machine, while GPU is high bandwidth machine. So to me, it kind of makes sense to just run it on GPU and yeah, faster.
But sampling involves random number generation, and that's kind of a sparse operation. So usually CPU, traditionally it was good to do that on CPU. So
need to get this offline.
okay, and the other question I had was, you said you were doing approximate top K calculation. Can you tell me the runtime complexity of your approximate top K algorithm? Or
which approximation?
there was a part where you said we are doing approximated top K selection, something like that. So what is the time complexity of that one?
I don't have good visibility on that too, but PyG uses FICE, so it basically pulls that feature from there.
I can say more. Okay. Great. Thank you, Aki. Okay, you are all set. Okay, super. So next talk is by Rishabh Ranjan, who's a PhD student in the computer science department at Stanford. co-advised with Carlos Gestrin and myself. And Rishabh will talk about RelBench, which is a benchmark for deep learning on structured data or on relational databases. Please take it away.
Hi, everyone. As you're introduced, I'm Rishabh. I'm a second-year PhD student here at Stanford, and I'll be talking about RelBench, which is a benchmark for deep learning on relational databases. I would encourage everyone to check out our website, which is relbench.stanford.edu, and also our GitHub repository, which is snap/stanford/relbench, and it already has 200 plus stars. It's very active, and people have been liking it so far. So Josh already had a talk earlier today, and he presented the relational deep learning blueprint. In this talk, I'll be covering the benchmarking and research infrastructure that we have around RDL. And then in the later part of the talk, I will be covering the empirical validation of RDL. So first, I want to touch on the benchmark and Python package. So RelBench is more than just a collection of databases. It is the complete framework to enable research on RDL. We support data loading, task specification, graph construction, model building, and in this part, we have tight integration with PyG and PyTorch Frame, as Aki mentioned in the previous talk. We have standardized splitting, standardized metrics, and finally, we provide a leaderboard to compare progress. We provide an easy-to-use Python package. You can install it with pip install RelBench. This Python package provides classes such as table, database, dataset, task, which allows you to express databases and machine learning tasks on them. We provide easy download infrastructure, so you can just download any existing RelBench dataset, get the database. We provide easy download infrastructure for the tasks as well, and then standardized splitting for getting the train, validation, and test tables. And finally, you can evaluate the predictions of your model on any task. We have a bunch of diverse data sets ranging from e-commerce domains, social networks, sports, and medical databases. These databases have rich schemas. So I have put two schemas on this slide. One is Rel Amazon, which is from the Amazon dataset, which has a table for review, a table for customer, a table for product. And then on the right-hand side, you have the Rel trial dataset, which is from clinical trials. And you have tables from, I don't know if you can read it, but like studies, sponsors, outcomes, facilities, and so on. And throughout the benchmark, you have table sizes ranging from 3 to 15. You have 74,000 rows to 41 million rows. You have 15 to 140 columns. And then we also have a lot of diversity in the time spans, ranging from 2 weeks to 55 years. Over these databases, we support real-world predictive tasks. One of those tasks, there are 3 kinds of tasks. The first one is entity classification. So examples would be predicting whether a user would churn in the next, let's say, 6 months for Rel Amazon, or predicting whether a user would earn a certain badge in the Stack Exchange database, or predicting the outcome of a study in the clinical trial database. The second kind of task is entity regression. Here, examples would be predicting the LTV, or the lifetime value of a user or item for the Amazon database, or predicting the click-through rate of an advertisement in the Rel Avito database, or predicting the position of a driver in the F1 racing database. And finally, we have recommendation tasks, where, for example, you want to predict the items that a user is likely to purchase on Amazon. You want to predict whether a user is likely to visit an ad in Rel Avito. And then for Stack Exchange, for example, you want to predict posts that a user is likely to comment on. So these are the databases and tasks that are available out of the box in RelBench, but RelBench itself is flexible enough to accommodate your own data sets and tasks. And in particular, we have detailed tutorials on our GitHub to showing how to use your own bases and define your own tasks in RHELbench. And moreover, once you've done this, you can run our RDL implementation by following the steps mentioned and running the scripts that are already there in the repo. If you do this, we would encourage you to contribute your databases to RHELbench. We have detailed guidelines for these too, and you can just make a PR with the requirements, and we'll be happy to incorporate them. Now, I would like to move to the next part of the talk, which is benchmarking RDL versus the current state-of-the-art approaches. The first part of this benchmark would be RDL versus single table baselines. So here is the table showing the results for entity classification. As you can see, the baseline here is light GBM. And we find that on average across the entity classification tasks, RDL is 20% better. The second, this slide has a table for entity regression. And here the baseline is light GBM. And we also have simple baselines like global zero, global mean, global median, and so on to make sure that our tasks are of good enough difficulty. And here again, we find that RDL is about 8% better on average. Finally, for the recommendation, the metric is mean average precision. Light GBM is the baseline. Then there's two simple baselines, global popularity and past visit. And we have two versions of RDL, one using GraphSage, the other using IDGNN. And here we see the most improvement coming up to around 300% better on average. And so the takeaway from these three slides is that there is important predictive signal in linked tables, and prior machine learning approaches which rely only on the predictive signal from one single table are losing out on this kind of predictive signal. And so relational modeling is very important. For the second half of the benchmark, I'll be showing our comparison of RDL with manual feature engineering. For this, we ran a user study with an expert data scientist, and manual feature is engineered by an expert data scientist is the prior gold standard for machine learning on databases. So for this, the data scientist we recruited is Alejandro. He's here today, if you want to grab him for a chat later. He has 5 years of industry experience with specialization in financial databases. And for this part of the user study, he was responsible for the full model building cycle. So in these slides, I want to show what a model building cycle looks like in order to enable a better appreciation for what RDL helps with. So if you're doing this in the traditional way, you maybe start off with exploratory data analysis, which can take up to 4 hours of manual work. You make some plots, try to analyze what's happening in your data. Based on that, you go to the feature ideation stage, where you come up with example features. That can take half an hour, maybe. Then you express those features in SQL and try to extract those features from the database. Writing such SQL can take like 5 hours. Once you have the features, you run a hyperparameter sweep on your tabular model of choice, for example, XGBoost, maybe another 2 hours. And finally, you do a feature importance analysis, and depending on that, you can iterate and have further cycles of feature engineering. And at the end of all this, you have a final list, in this case, of like 54 features. It took around 12 hours of high-quality expert work, around 700 lines of code just to solve this one new additional task. And RDL doesn't have to do any of that. But despite that, RDL is able to match or outperform manual features in 11 of the 15 tasks that we compared in our benchmark. So here, the green bar is RDL, and the orange bar is the data scientist features. More importantly, RDL is able to match or outperform the predictive performance despite taking a lot less manual effort. So in this slide, manual effort is measured in terms of human hours, and RDL requires 96% less human hours, going from 12.3 hours roughly for the data scientist to 0.5 hours for RDL. And then if you measure manual effort in terms of lines of code, then RDL reduces the new lines of code by 94% on average. Yeah. So the takeaway from these last few slides is that RDL overall gives you better predictive features with much less manual effort. So our paper on RelBench got accepted into NeurIPS 2024. Please check it out. And that's the end of my talk. I would, again, point you to relbench.stanford.edu and our GitHub page. And I would also like to take this opportunity to say that we welcome community contributions to RelBench. So please help us improve if you can. Thank you, and I'm open for questions.
Great. Thank you, Rishabh. Any questions?
Hello, very interesting presentation. I see the comparison about the RelBench versus the manual expert, but it looks like it's compared to GNN with light GBM or tree-based model. Do you have numbers about compare with GNN with GNN expert to use the same data set, create the graph neural network graph, and do the performance manually?
I don't exactly know what you mean by GNN expert, but...
Yeah, okay, let me explain a little bit. So for the RelBench, it's a data contains a lot of correlations among different tables. So for the performance of the final prediction, the relation among those tables may play very important roles in the model. So I think the backend will be use some GNN models to handle this information. For the comparison, the human beings just use manual features and use a tree-based model as the base model. So my question is, have you ever compared the RelBench with another expert who is good at GNN and also create data in the graph format, then use the graph neural network to build the model and do the comparison?
I see. I think I understand your question. That is a very interesting comparison, but we did not do any such comparison in our user study. So our data scientists mostly always used tabular machine learning models, not GNNs.
Yeah, maybe if I add, right, like if you'd want to do this, then you would need to take your relational data, spin up a graph database in which you would go from tabular representation to the graphical representation, and then you'd need to write the GNN layers to learn on top of that graph database, and then do the hyperparameter tuning. I think in these experiments that we showed, there is actually still quite a lot of room to improve the GNN part. To work with to kind of improve the architecture, the kind of the hyperparameters to further boost performance. So that's one way to think of this. Yeah, but thanks for the question. One more?
Hi, I'm Malham with Relational AI. We're huge fans of the work and the community. Nice talk, thank you. So I'm sure you've thought about this, but in the past when we've looked at Kaggle data sets, in general, the structured data doesn't become normalized. It basically, you get a data frame and all the features, and that's where you're forced to start. Is there a way to take these data sets, move them to Kaggle, and create some kind of competition, so we're not having to pick on poor Alejandro here as the baseline, and then see what are the best models that the black belt Kagglers can generate with features, And then what are the best models the same community can generate with GNNs? Because as you said, there are different approaches to doing it with GNNs.
You want to go? I should go. Good suggestion. So suggestion is to run Kaggle competitions. I think there are several answers. I think first answer, basically, Kaggle is not the real world, right? And
sure.
usually what Kaggle people do, you cannot put in production. It's so custom and so fine-tuned on that data set that it doesn't kind of lead to real insights. I think is the learning from the industry. Some of the data sets here are actually coming from actual Kaggle competitions. And there, what you learn is that the GNN-based approach scores in top 1% to top 2% of 3,000 solutions that people have pushed, right? So this means you are as good as somebody who spent 2 months or 3 months tuning the model, doing feature engineering, training 700 different models, ensembling them all kinds of different ways, to push up those performance here with a single unified architecture. But I think maybe what you said also I think is important. You kind of said, these Kaggle data sets are kind of very stylized, and I couldn't agree with you more, right? So in the real world, I think the benefit of this will only be bigger because you don't get a predefined data set, you don't get a predefined label, but you actually have to select the data you are training over, right? And if you have to select the data, do the feature engineering and all that, then you can only iterate and explore a very limited amount of the data. Now, if the modeling part is, if you can iterate 20 times faster, it means you can explore 20 times more data, and you can really find the data in your data warehouse that actually makes the difference in that predictive problem you are trying to solve as a data scientist in an organization. So I think the value actually comes from ability to iterate quicker, because data scientists, like in the real world, you are not solving a Kaggle competition. You first have to come up with a Kaggle competition, only then solve it. But yeah, that's a great point. Anything else? Good. Thank you so much for the questions. Thank you, Rishabh. And then next speaker will be Rishi Puri from NVIDIA. Great. Thank you, Rishi. I like your shirt. Very beautiful. Great. So Rishi comes from us to NVIDIA. He will be talking about integrating GNNs and LLMs, and also how we are able to do this inside PyG. Let's just.
I'm an engineer.
NVIDIA is investing a lot in CUDA drivers, but not enough in GPU drivers. Sorry, let's be patient.
Sorry, guys.
It's okay. It's okay. Why does it?
I need to re-sign into the Wi-Fi.
Sorry. Okay. Amazing. Great.
Sorry about that.
We have the slides. Rishi, take it away. Yoo-hoo.
Well, hello everybody. My name is Rishi Puri, and I am a senior deep learning engineer at NVIDIA. You wouldn't think that with my technical difficulties, but I swear I am an engineer. Today, I will be talking to you about GNNs and LLMs in PyG. So modern LLMs are built on the transformer model and excel at predicting the next token in a sequence. A transformer layer can be viewed as a fully connected GNN, where the importance of each connection is learned. As such, GNNs are ideal encoders for data where the relational structure is given. In contrast, transformers end up using orders of magnitude more parameters than GNNs to learn these relational patterns based on attention. Generally, in traditional machine learning, using less parameters to achieve equivalent or better results implies a more general model that may hold out better in the wild. GNNs can improve LLM accuracy by adding semi-orthogonal information. Since LLMs are so much larger than GNNs, adding GNNs comes at almost no computational cost. For example, when using a 7 billion parameter LLM with an appropriately sized GNN, the LLM can take close to 99% of the time with GPUs like A100 or H100. The latest release of PyG comes with new GNN plus LLM features as one of the main updates. There are 3 new major GNN plus LLM features in PyG. First is the GRetriever model, which allows a user to easily combine any PyG GNN with any Hugging Face LLM for graph-based RAG tasks. Below is a sample code snippet showing how easy it is to use a GRetriever model. The next feature is the Web QSP dataset for RAG question answering with knowledge graph context. The final feature is an example for how to train a GRetriever model on the Web QSP dataset. By default, this example uses a Llama 2 7 billion parameter LLM with a Graph Attention Transformer GNN, or GAT. There is also a tiny llama flag for using a 1 billion parameter model, but you can easily swap in any Hugging Face LLM. In general, GNN plus LLM workloads are very compute intensive, and therefore GPUs are essentially a necessity. Running on CPU will basically never finish. In this case study, Neo4j used Stark Prime, a medical knowledge graph dataset made by Ure's Stanford group. Neo4j was able to use GRetriever to achieve more than double the top benchmark hit at 1 metric. Check out their poster at Happy Hour for more information. This is very impressive results in my opinion. So this diagram here depicts a general graph-based RAG workflow using GNNs as a prefix to the LLM's inputs. We start with a natural language query, which needs to be encoded by our LLM's tokenizer and encoder. We also need to use the query to retrieve a relevant contextual subgraph from a larger knowledge graph database, and then encode it with a GNN. We then want to combine the embeddings from the GNN and the LLM encoder. Finally, we pass this into the LLM's decoder module to get our final response. There are also new graph-based RAG features coming soon to PyG. These include improved abstractions for indexing your knowledge graph and retrieval from it. This PR includes tooling to easily profile the compute performance of these systems. Check the GitHub link for more details on this work. This work is already available in our GPU-optimized NVIDIA PyG container. See the link for details. Now, in many real-world RAG settings, you do not have a pre-made knowledge graph from which you can easily pull. This PR adds a text-to-KG class that converts raw text documents into a knowledge graph using an LLM. Below is an example of how you could use it for converting a traditional RAG dataset, which usually has questions, answers, and context paired together. The PR uses NVIDIA's latest 70 billion parameter model via NVIDIA Inference Microservices, since many PyG users can't run such large models locally. Since the knowledge graph is at the beginning of the graph RAG pipeline, the quality of its information is essential, and using smaller, lower quality models may impact your downstream accuracy. That's why I chose to use this 70 billion parameter model, which is supposed to be on par with or better than the much larger GPT-4o based on several benchmarks. So the idea of using GNN embeddings as a prefix to transformer sequence models is a highly general one and can actually be extended to many modalities and applications. For an example, OGBG Code 2 is a dataset from the Open Graph benchmark that consists of abstract syntax tree graphs for Python functions. The task here is to predict the names of the function based on the graphs. In this PR, I have augmented the dataset with the matching raw Python functions, removing the function names to prevent the model from cheating. The example in the PR shows how to train a GRetriever model for this task. The current state-of-the-art approach on the leaderboard uses only the graph data. By combining graph and text data with GNN plus LLM, we can triple the state-of-the-art F1 score from 0.2 to 0.6. Now, mind you, this original state-of-the-art F1 score basically represents a GNN system that is inaccurate more often than not, while the GNN system we have is accurate a majority of the time. Another example is our community sprint. The goal of the latest PyG community sprint is to expand GNN plus LLM features to support the sciences like biology and chemistry. Check out the linked GitHub issue, which tracks the community effort. Currently, there are 4 projects going on to integrate techniques from 3 biology papers and 1 chemistry paper using GNNs and LLMs. It's still not too late to contribute to the community effort. As Akihiro mentioned, please reach out to us on Slack or GitHub. Now, the possibilities here are truly endless. As another example, one could imagine a setting where a business leader could ask an AI general questions about their customers. This idea can be further extended to use multiple modalities for a single task. Imagine an Amazon product graph where each node has a text review and a photo. Extending it even further, one could use highly heterogeneous graphs, such as the ones used in RHELbench, where node and edge features could be anything like text, images, audio, video, and more. So now for a change of pace, up until now, we have been talking about GNNs feeding LLMs. However, for graph-based tasks like node classification, we actually want an LLM to feed a GNN with text-based features. The state-of-the-art method here for node classification on the OGB leaderboards is the GLEM algorithm. Due to memory limitations, training a full end-to-end system where an LLM provides textual embeddings for every node is essentially impossible at scale. As such, GLEM lets the LLM and the GNN take turns iteratively improving each other based on the learnings of the other in an alternating process. The implementation of GLEM in this PR is about 7 times faster than the original paper's code using the same hardware. This PR introduces the new text-attributed graph interface, allowing users to explore and create their own data sets. It also adds optional support for LLM fine-tuning using LoRa from the PEFT library, which is part of Hugging Face. You can check the GitHub link for more details. This work is also already optimized and available with our NVIDIA PyG containers. So, in conclusion, the latest PyG features are the easiest way to use GNNs with LLMs. NVIDIA provides all of the latest PyG features optimized for NVIDIA GPUs packaged in a Docker container with effortless out-of-the-box experience. You won't get what I had when starting this talk. The NVIDIA AI Enterprise subscription provides the highest level of security, reliability, and support for companies looking to bring AI into production. The latest version now includes DGL and PyG, and please check out the link if you're interested. As a final note, I want to acknowledge our interns for their contributions to this effort. Thanks to Junhao for his excellent work on GLEM, and Zachary, who's sitting over there, for his efforts on adding new APIs to PyG for profiling, indexing, and retrieval for graph-based RAG tasks. Thank you. To discuss further, come by my poster during happy hour. Seems we might have a little time for questions.
Great job. We have time for a question or two. Maybe I will ask you a question. So this idea of kind of feeding the GNN output as a input to the LLM, can you say maybe more to the audience how you train that the GNN and the LLM are kind of speaking the same language?
Yeah, so there's really 2 options based on your computational availability. But generally, the end-to-end approach where you fine-tune both the GNN and the LLM will generally do better, just like, you know, in RDL, if you do a full end-to-end approach or computer vision, anything like that, we generally assume it'll learn better. But if you don't have the resources to train your LLM, like we said at the beginning, the GNN is super small and most people can train it. And so you can essentially fine-tune the GNN to speak the language of the LLM encoder. And so without fine-tuning the LLM, you can teach the GNN to essentially create tokens that represent some higher order multi-hop logic about your knowledge graph. But again, end-to-end with more compute is generally the better approach. It's for each use case, yeah.
Awesome. Thank you. Anything else?
No, so
maybe repeat the question. The question you said you're replacing the token embeddings with the output of the GNN.
yeah, so if you, at this step, basically, we're gonna prepend basically the GNN outputs node embeddings, and we do an aggregation to get a singular vector. And then we're gonna prepend that to the LLM's encoder outputs. And so it's essentially like, you know, in RAG, you would prepend it with textual context or a vector. In this case, the token or vector is a GNN's interpretation of your knowledge graph, essentially. Yeah.
Awesome. Thank you again. So we have a half-hour coffee break, and we will start at 11 a.m. Pacific time. Thank you so much.
Okay, it's set up.
Okay. Oh wow.
Yeah. So,
Great job. Great job.
yeah. Cool.
Maybe I can make a joke.
Oh, actually, let me see if I can have a.
Great. So welcome back from the coffee break. It's time to start right on time. So this second session, the theme will be in biomedical discovery. We'll hear about agents and some large-scale foundation model training. And the first talk will be by Kexin Huang, who's a PhD student in the computer science department at Stanford. And he will talk about a collaborative project between Stanford and GSK, a pharmaceuticals company, about a very important technological advancements in genome-wide association studies that allows you to apply GWAS to much smaller sample sizes and get much better statistical power out of it. Thank you, Kexin.
Cool. Thanks, Yuri, for the introduction. Hello, everyone. I'm Kexin. I'm a fourth-year PhD student working with Yuri. So today I'll talk about our project on using this graph learning on over massive functional genomics knowledge graph to do small cohort genetics discovery. So this joint work done with an amazing set of scientists from Stanford AI, Stanford Genetics Department, CMU, ARC Institute, and also our industry partner, GSK. So I want to first start with a brief review of what is a human genome. So the human genome basically encodes the blueprint of our body. You can think of it as like a text file of 3 billion tokens of A, C, G, and T, and it basically instructs everything from the cellular functions and all the way to your complex traits like your height, your hair color, and also your health. So not everyone has the same copy of genome, and there's kind of these small differences between from person to person. And these small differences is also known as a genetic variant. And so, for example, here, this is a variant which is usually denoted as this RSID, and it's located at the 55 million-ish position at the chromosome 19, and it has a mutation from the T to become a C. So there's lots of these mutations happening for each one of you, which makes you unique, and also makes you susceptible to potentially some diseases. So for example, this variant that I was talking about is actually a very famous, well-studied variant called E4 allele. This variant will lead to kind of a protein conformation change and leads to increased amyloid beta, which leads to Alzheimer's disease, which is one of the most prevalent diseases in the United States, causing 6.9 million cases. And there's numerous these kind of variants associated with the disease that can cause the disease. So the central task of drug discovery is just to find this kind of right variant for the diseases. The reason why it's so important is because in order for you to develop an effective drug, you first need to understand the mechanism of the disease clearly. And finding the right genetic variant of the disease is the very first step. And it's also a very important step. Actually, one of the leading causes of failure of clinical trial is actually a wrong target. So if you have a wrong target and you spend so much money to develop a drug, you're wasting like 10 years and billions of dollars. So you really don't want that to happen. So this is the kind of central question that we're interested in investigating, that is how to find variants out of these 3 billion options that are associated with the disease. And this is an extremely difficult task, right? Imagine you have a 3 billion character text file, and you want to find a few single typos. It's really like finding a needle in a haystack kind of thing. So this task is extremely important in the drug discovery domain. And there's existing work that has been done for the past 20 years, and it's called Genome-Wide Association Study, or GWAS. So the intuition of GWAS is actually pretty straightforward. Basically, if you're interested in looking at one mutation from this C to T at this specific position, you'll collect patients with the disease and collect patients without the disease, and then you basically count the number of patients with the disease, how many of the variants are there in the disease patient cohort, and similarly, you count the number of variants in the healthy patients. And you can really compare the difference between the disease frequency of that variant and the healthy frequency of that variant and see if there's a significant enrichment. And there's a kind of a hypothesis testing framework to produce a p-value that measures the variant association to the disease. So that's kind of what is basically the GWAS. And you will do that for millions and millions of variants. And you will produce a kind of this kind of plots where you will see a peak if there's an enriched signal of variant disease associations. So just to be a bit more concrete here, the output of GWAS, it will be a summary statistics file looking like this. So you have basically the important columns here is the ID, which is the variant ID, and then the p-value, which is measuring the variant association to the disease. And because we're scanning millions of variants, usually we do a 5e-A, like genome-wide significance threshold, to see the variant is like associated, the set of variants that are associated with disease with high confidence and force discovery control. And another representation is the Manhattan plot, as I mentioned before, where the y-axis is the minus log p-values, and you can see a peak if there's this variant is has very low p-value, for example, below the 5e-A threshold. Cool. So that's a very brief introduction to what is a GWAS. So GWAS has been applied to many, many diseases of interest, and everyone is kind of trying to apply GWAS to their own kind of drug programs. And in total, it has identified thousands of variants for common complex diseases. And there's also a recent article trying to say the impact of GWAS for drug discovery, and it's estimated that the probability of success for drug mechanism with genetic support is 2.6 times greater than those without. So that's why every kind of pharmaceutical company are extremely interested in this human genetics and have a big department of geneticists. So okay, so now hopefully I've convinced you that GWAS is really important and is great. So what is the problem? Why are we kind of want to develop a new method here? So the key problem of GWAS is like it requires huge sample size. There's numerous reasons for that. The two main reasons, like the variant for GWAS is usually have small effect size, so it usually requires a large sample size to detect this kind of tiny variation with high confidence. And there's also, because we're scanning millions of samples, variants, we need a very stringent multiple hypothesis testing adjustment. So this is usually we require a huge number of sample size in orders of tens or hundreds of thousands. But actually, when we really wanted to deploy this GWAS method to the disease of interest, where we find that the disease of interest usually have extremely small sample size. So for example, rare disease. In total, we have 7,000 rare disease, and 90% of them have no effective treatments, and most of them we don't know the underlying genetic mechanisms, and it collectively impacts like millions of patients. So applying GWAS to this small cohort in, like, for example, rare disease is often have the most impact, but it's also what GWAS currently cannot do. And similar, and I guess other than rare disease, also many common disease also does not have this big cohort because there's cost in collecting the disease sample and there's data privacy and consent issues. So for these kind of diseases or these small cohort settings, we really need a more data-efficient method for identifying these variants. So just to be concrete, I guess for the AI kind of task, what we aim to do is we take in a GWAS summary statistics. We have an AI model that can produce a new summary statistics, where we will produce a new p-values for each variant, and this new p-value should have same level of forced discovery control, and also ideally should have abundant novel discoveries, especially in the small cohort regime. So now I'll talk about our method. So basically, if you look at the original GWAS method, the GWAS basically scans through the genome one at a time, one variant at a time, only looking at the genetic information. And because it is, when there's a small cohort, we definitely need to solicit from other kind of information. And recently, there's a burst of this kind of functional genomic screen that mapped the molecular function of a variant. So for example, from variant to gene, there's like QTL studies, there's CRISPR experiments, there's Hi-C data that kind of clearly mapped the variant's functions to the correct genes. And there's also historically abundant data around gene to genes, including physical interaction, inhibition, binding, and so on. There's also gene to program data like perturb-seq pathways, and so on. So these map the kind of the relational information from that contextualize the variant to the molecular context. And also, there's also variant annotations. There will be like methylation status, chromatin accessibility, and also recently there's a burst of foundation model embeddings that can annotate the variant to give some informative information about the variant. And there's numerous data resources scattered across these different databases to map these variant functions. So intuitively speaking, why would this data help? So imagine if you have a variant, if you know beforehand, this variant is in a region that is known to be functional, for example, it's in an open chromatin region, then we have increased prior that this variant should be associated with the disease. And also, there's also a lot of this relational prior. For example, if a variant is, if we look at the local neighborhood, that's this molecular context of the variant, and we see that there's like a few genes or programs that are known to be associated with the disease, then we also have an informed kind of increased prior of disease associations. So I think our method KGO is basically we want to utilize this information to boost the GWAS power, especially in small cohort. So now I will delve into our method, which is called KGWAS, which stands for Knowledge Graph GWAS. So the first step of the method is, because basically if you, as I mentioned, there's so much functional genomics data, but they're all coming from different experimental data. They're coming from different experimental screens. And we provide the first resource to map the genome-wide functional genomics data, and everything, every different kind of experimental data can be consolidated into one place, which is a knowledge graph. Where in the knowledge graph, there will be 3 types of nodes. Like there's a variant, there's a gene, there's also the gene programs. And then there's also this relation which is defined by each individual experiment data. So this kind of represents the first genome-wide variant to gene to program knowledge graph. And in addition to the relational information, we also curate lots of annotations for the variants, including the epigenetics profile, and also similarly for the genes, including single-cell RNA experiments. So given the knowledge graph, we want to now create a method that can distill a knowledge graph prior, which measures the variance prior based on the knowledge graph information. So we develop an objective function to compute this knowledge graph prior. So the basic step is we first train graph neural networks to fit the GWAS association to nodes and edges. So this way, the node embedding and edge embedding implicitly should capture the GWAS association. And then the step 2, we will predict the variant association for every variant based on the knowledge graph information. You can think of it because if you look at the variant, if you look at get the local 2-hum neighborhood, it will basically picks up how much this local neighborhood has enriched disease associations. And this predicted variant association can be used as this knowledge graph prior information or prior score that can be used to adjust the p-values. And the last main module of the framework is a covariate-based p-value weighting framework, because for GWAS, there's lots of, we're scanning millions of variants, so forced discovery control is essential. You don't want to create a method that just gives you lots of false positives. So we utilize a statistical technique called a p-value weighting from this paper, where it dynamically adjusts based on the covariates, which is knowledge graph prior, to generate a new p-value, which we call a KGWAS p-value. And this KGWAS p-value is used as the new summary statistics of the method. Cool, so that's kind of a brief overview of the method. Now I'll delve into the extensive kind of result that we have. So the first set of results is around the statistical simulations, because we want to show that our method controls the false discoveries. So we first kind of run extensive statistical simulations where we try different configurations of the genetic architectures and so on to see the model's performance at different scenarios. And we see that across the board, we're able to achieve the similar level of false discovery as the base GWAS, while have more discoveries in a causal simulation where, So, but simulation is still kind of a simulation. It has lots of assumptions. So in our case, we were really interested in finding a framework to rigorously evaluate the small cohort if we can identify more hits, more discoveries. So we leverage a UK biobank, which is a big data set, consists of around 500K patients with raw genetics data and also lots of phenotypes. And what we do is that because we're interested in small cohort, we can basically downsample the large cohort to a small cohort of any size of interest. And then we run the GWAS and KGWAS on a small sample size. And where we have a list of discoveries. And we can check if this discovery can be replicated when you have much, much, much larger sample size. So this way we can rigorously evaluate, and also in a systematic way, about the discovery in a small cohort if it's real or not. And we can do that for any kind of a number of traits. So we run that across around 20-ish traits, like independent traits. And we're able to see that our KGWAS method actually discovers 90% more, like up to 90% more replicable discoveries than GWAS at 1,000 sample size. So this is a significant increase over the base GWAS. I guess on another view, we can also interpolate the number of sample size required by KGWAS to achieve the same number of discoveries as the base GWAS. And we're able to see that KGWAS is actually up to 2.6 times more data efficient than GWAS. For example, KGWAS only required 355 samples to get the same number of discoveries for GWAS at 1,000 samples. So this means that for genesis, you don't need to recruit such a large number of samples. You only need to recruit 2.6 times less sample size. So this really facilitates the discovery process. So now we kind of established that our KGWAS method is like rigorous and also can have lots of power improvement in this kind of systematic evaluations. Now we really want to apply it to a large number of small cohort diseases to see if we can identify novel genetic insights in a systematic fashion. So we curate a data set of 554 diseases with less than 5,000 cases. And notably, among them, 144 or 25% of diseases actually match the rare disease prevalence. So these are kind of rare diseases where most of them do not have much hits, much known genetic understandings. And you can also see that these 554 diseases covers all the major disease areas, all the way from like cancers or nervous system and so on. Cool. So this is a summary result of our KGWAS applied to this large number of diseases. Overall, we're able to make 576 discoveries, and each of them could be interesting and translates to potentially some drug programs. And this corresponds to a 56% increase over the base GWAS. And you can see that the improvement is like consistent across all the disease areas. And notably, we are very excited to see that actually KGWAS is the most has even more improvement in the rare disease. For example, in this 144 rare disease, KGWAS has 80% more discoveries compared to the average 46% here. And another thing to look at is look at the diseases with these 0 hits in the original GWAS. This means that if KGWAS can find find 1 hit, then it potentially leads to initial understanding of the disease mechanism of these diseases. And we're able to do that for 92 diseases in this 500-ish diseases. So overall, I think we can conclude that KGWAS greatly expand the genetic discoveries across a wide range of diseases in a kind of consistent fashion for both rare and common diseases. So here I want to look at kind of 2 examples to really show that the KGWAS disease, discoveries are not kind of random. They are actually align a lot with the functional evidence. So the first example I'm looking at is ulcerative colitis, which is not a common disease, and there's no effective treatments, and it affects many patients in the US. And for the UK Biobank, there's around 4,000 cases. And we apply KGWAS, and we find this novel variant at this position, which is not significant in the base GWAS, but is significant in the KGWAS. And we go ahead and do this kind of functional evidence research, where we first find that this variant is actually EQTL of this gene. And this gene is actually a known kind of immune gene that can potentially regulate the colitis disease. And then we also, to our surprise, we also find that actually there's an independent study published in Nature 2020 that explicitly knock out the region of that variant and see the phenotypic changes in the colitis. And we find that actually, and they find that this variant actually has significant impact on the colitis histological scores. And I guess another example that I want to give is on a real disease, which is called myasthenia gravis. this is a true rare disease, and it leads to lots of symptoms like difficulty swallowing, double vision, unsteady walk, and there's no effective treatments, there's unclear mechanisms, so it's a very important rare disease. And in the UK Biobank, there's a 358 cases, and then we apply it to KGWAS. And we're also able to find one variant that is kind of missing in the base GWAS, but is kind of significant in the KGWAS. And we find that this variant is enriched in neuron-related cell types, which is a kind of a known related cell type for this MG pathogenesis. And also, this variant is an EQTR of this gene, and we did some research and find that this gene is actually involved in this epigenetic silencing by this complex, and this complex is known to cause symptoms that are similar to this MG disease. So these two examples hopefully show that this KGWAS variants, they align really well with the functional evidence out there. So KGWAS actually also have many other downstream genetic applications. For example, because we're using a graph neural networks to fit the GWAS association over the knowledge graph, we can learn a disease-specific knowledge graph. And we use a graph interpretability or explainability technique to reconstruct that. And we find that this GraphXAI prioritized network actually have overlap a lot with this orthogonal evidence. And because GWAS is so fundamental for the past 20 years, there's lots of methods building upon GWAS. So if we have a better GWAS method, then you can just simply connect with the other method and see if the performance kind of increase as well. So for example, we connect the GWAS summary statistics to Magma, and we find that it is able to identify disease-critical genes in a much better, much higher accuracy compared to the base GWAS. And also, we also to connect to SCDRS, which is a method to detect disease-critical cell populations. And we're able to see it can detect novel clusters of cell population that is missed by the base GWAS. And there's more in-depth kind of analysis in our paper. So cool. So that's all of my talk. So we actually released the UI today, which is at kgwas.stanford.edu, where you can explore for your disease of interest. And also we'll release the preprint and GitHub very soon. And I want to thank again for all my collaborators, and thank you.
Thank you. Super cool. Any questions?
Great talk. I have two questions. So the first is, have you guys done any ablations to look at what aspects of the knowledge graph are most useful for getting better performance over more traditional methods?
Yeah.
I know a lot of people in the omics community think that incorporating cell state information from omics might be really helpful, and I'm curious for you guys if that seemed to be a difference maker.
Yeah.
And the second question I have is that a lot of indications or traits in the UK Biobank are really correlated with each other. It sounds like you guys have incorporated knowledge about interactions amongst things like genes. But I'm curious if you guys have played around at all with interactions among the outcomes that you're trying to predict, and if it's useful for predicting things for rare disease, right? So it might be that rare disease individuals present with certain blood pathologies that are measured in a lot of individuals in the UK Biobank, and maybe leveraging that information at the level of hundreds of thousands of people can help you better understand those really rare cases too.
Yeah, I think that's two great questions. So for the first question, actually we have done extensive ablation study in the paper. So maybe a few kind of important factors. The first one, we try to permute the knowledge graph structures. So just to try to see if the knowledge graph indeed have this structural information. And we find that if we permute that, actually the KGWAS just becomes similar to GWAS. So that means that the knowledge graph structure, this relational information, is kind of the most important thing. And we also ablate on the individual relation types, and also remove for example, the variant annotation and the cell annotation, and also try various different alternative variant annotation and cell annotations. And we find that our recurrent version is the most the best kind of combinations basically. And I guess the last thing is we also try to scale the knowledge graph, because we can randomly remove a fraction of the knowledge graph into like 10%, 20%, and 50%, for example. And we'll see that as the fraction goes larger, the performance just goes larger and larger. And I think this also is interesting because it can potentially hint at like a scaling law, like in some sense. If we add, because functional knowledge graph still is very, very vastly incomplete. So if we add much, much more data, it should ideally improve and improve and improve. So yeah, hopefully that answered the first question. And then the second question around the related disease. So I think we actually, initially we also tried a version which is using multiple diseases. I think definitely improved power. But I think the technical thing, a challenge is like, it's very hard to gauge the real improvement in some sense. Potentially for some disease, there's related disease, then you can improve the performance. But some disease is not, then that's very hard. So that's why in our first version, we're interested just looking at the molecular kind of function, which is independent of disease, and try to take in GWAS summary statistics, and then you can just learn a disease-specific thing. But I think in the future, potentially, you can integrate that. Yeah.
Thanks. Awesome. We have to end here. Thank you so much, Keshin.
Thanks.
So the next speaker is Yusuf Rouhani, who's a computational group lead at the ARC Institute, which is a biomedical discovery non-for-profit research institute adjacent here to Stanford. And Yusuf will talk about his research on AI agents for biomedical discovery.
Thank you. Thanks, Yuri. Hi, my name's, as Yuri mentioned, I'm Yusuf Rouhani. I lead a machine learning group at the ARC Institute, and I'm really excited to be here to talk to you about AI broadly for biological discovery, and in particular, I'll go into a bit more details on an AI agent that we developed for designing biological experiments. So I'm sure I don't have to convince anybody in this room that AI has really transformed all aspects of scientific research. There have been many great talks this morning, and there will be many more later today that will present many more examples of this. One example that I like to kind of walk through a little bit is AlphaFold. So what AlphaFold does, again, I'm sure most of you are aware, but just to get everyone on the same page, AlphaFold predicts for you protein structure from sequence. So you provide to this model the sequence of a protein, and it predicts for you what the structure of that protein would be physically. And the way that this works is it's trained on experimental data from actual experiments where protein structure has been measured. And then using AlphaFold, what you can do is you can begin to infer the structure for additional sequences that you may not have seen when you were training the model, but you're able to make inferences for. And so this is obviously a very exciting discovery. As I'm sure, again, most of you must be aware, this won the Nobel Prize in Chemistry just a few weeks ago. And it's really startling because this was just released 3 years ago. And so it's very, just the amount of impact has been so tremendous that it's already been awarded. But if you look at AlphaFold by itself, it's actually not usually performing the entire discovery process that is associated with, say, protein structure prediction. Usually when you're performing the protein structure prediction task, you're interested in optimizing for a specific property or identifying a protein that can potentially perform a specific task for you very efficiently. And this is, so in some ways what you can think of this is essentially, this is really talking about the search problem. So if you have all these predictions coming out of AlphaFold, the next step is usually kind of going over the space of these predictions and trying to identify what protein is actually most optimally achieving the task that you're most interested in. And so one way to sort of abstract this is a lot of scientific discovery is interested in this search problem, where we want to be able to explore a hypothesis space and identify specific experiments that would be most informative and most useful for us to try out in the lab. And so what I like to think of when I see biological discovery and AI is really kind of compartmentalizing approaches into these two kind of different directions. The first is where you're essentially looking at existing experimental data, analyzing it, and developing new insights from it. And the second approach is where you're kind of thinking ahead. You're trying to perform that search function. You're trying to generate new data and really enhance the models that you already have. And so this second direction is what I'll be presenting some results for today. And this is really where I think there's a lot of exciting work that AI can do to really kind of push the frontier. And another way to also talk about this is on the left here, you're talking about AI for representing biology, and on the right, we're thinking about how we can design biological experiments using AI. And scientists aren't the only people excited about this. So Dario Amodei, who is the co-founder and CEO of Anthropic, a few weeks ago had a blog where he said that the right way to think about AI in biology and scientific research is not as a method of data analysis, but rather as a virtual biologist who performs all the tasks that normally biologists do. And so this involves like looking at results from an experiment, forming new hypotheses, running new experiments, and then sort of updating your prior beliefs and sort of doing this iteratively. This is what is normally involved in the process of scientific discovery as a biologist. He further goes on to claim that if we did this effectively, AI-enabled biology and medicine will allow us to compress the progress that human biologists would have achieved over the next 50 to 100 years into 5 to 10 years. Now you can disagree with him if you like, but I think what he's still capturing is this idea that there's so much kind of so much that we're leaving on the table in terms of what AI can do for us, in terms of really accelerating scientific discovery, and this is really moving beyond even like the paradigm change that AlphaFold and other AI models have already achieved. So this is a really exciting space to be working in. But if you continue reading his blog, he also describes why this is happening, right? So why is it so challenging for us to do this at a fast rate currently? And one of the main reasons for that is that biology is complex, and it's very difficult for existing approaches, existing computational and human approaches, to be able to identify the right experiments to perform, the right data to generate, the right models to be able to train for really guiding the scientific process. So what we did in our work is we looked at a very specific instance of this. We looked at genetic perturbation experiments, and we kind of tried to model this exact same problem. So here what we're trying to do is we take a specific gene, we knock it down, and we measure its phenotype. And this could be very valuable. For instance, if the cell, say, is experiencing a specific disease, and you knock out a specific gene, and you observe that the phenotype associated with that disease is reduced. So then that can give you a good hypothesis for what might be a useful candidate for a drug. So this is really often the second step after what Kishan presented in his last talk, where he was describing GWAS. Usually after the GWAS experiments, they'll perform actual experiments to test out what these genes do. And so this is a nice example of how this kind of fits into that drug discovery process. But the challenge, as I mentioned previously, is this is a very complex, large space. You have various different genes within the, even just within humans, over 18,000 of them. And out of this very large set, there's only a very small subset, usually about 5%, maybe 300 or 400, that really show that phenotype that you're interested in. So how do you effectively search this space and target these interesting genes without having to waste too much resource on experiments that may not be valuable but still cost money? So the usual approach, even if we disregard AI, has been to sort of design iterative experiments using some kind of a strategy that optimizes for detecting these genes. So essentially, you break down your experiment into small batches of, say, 100 or so genes in each experiment, and then you try to iteratively move towards where you think that interesting phenotype might be. But this has a number of challenges. Most importantly, you really have to have a good understanding of that complex biological landscape that I showed you a few slides ago. You also need to be able to balance your prior knowledge of biology with what you're getting from these experiments, right? So as you gather more evidence, you have to be able to weigh that new evidence with the prior knowledge that you have of biological processes. And finally, whenever we try to develop these computational models, biologists are only really satisfied if we have good interpretability. So how can we make these models more interpretable, more accessible during this discovery process? And so we propose using large language models as AI agents that can guide this process. And the reason that we propose this is we believe that AI agents, I mean, we've seen through experiments that AI agents have a lot of prior knowledge of biology. They've been trained on the scientific literature. There's been work that shows that they're able to parse through large amounts of data. So if you feed in a big table, they're able to understand what's going on, what the core values are, what trends they can observe. And finally, there's also evidence showing that they're able to reason and make decisions about what is the right next step to perform. So all of these capabilities together give us the motivation to really explore agents as a potential solution to guiding this biological experimental discovery process. So more tangibly, the way that we perform this is we have an agent and we have lab experiments in a closed loop. The agent proposes an experiment, which is sent over to the lab. At the lab, the experiment is performed. The results are then fed back to the agent, which then processes this result, makes a decision about what the next step should be, and this is continued on iteratively until we arrive at a satisfactory goal, depending upon the goals of the experiment. Okay, so now let me kind of dive in a little bit deeper on what I mean by agent and how this input and output is processed and what performance we observe. So the agent is a loose term for a large language model combined with a number of different tools. So here I highlight some of them, which is like literature review, gene search, agent critique, and we've also experimented with a few more that I haven't shown here. And then the way that the agent works is that it takes as input the output from the previous experiment, and it tells you what the action should be in the next experiment. Now, we've carefully designed this input-output format such that the agent is able to effectively and reliably produce an output that is meaningful. And so let me show you how we do that. So the initial prompt that we provide to this model is, you are a helpful research assistant, so that's defining its role. I'm running a CRISPR screen or a perturbation screen to identify genes that regulate the production of this specific phenotype. I need your help to decide which genes to perturb, so the task has been defined there. And then here are some past observations. So here's some evidence that I've already gathered for you to work with. And so that's the past results. The response from the agent, excuse me, is also forced to be within a specific structured format. We force the agent to provide a reflection or a reasoning on why it made the specific choice. So was there a specific biological process or a pathway that it felt was very relevant in this specific setting? Or is there some other reason why it thinks it should perturb these genes? It also is forced to provide a plan, and this plan is maintained across multiple steps. So here we are kind of forcing the agent to be a little more long-term in its thinking, and so not just think about the immediate step, but also try to plan ahead for the next few steps. And then finally, it provides the actual solution space, which is the set of actual genes or experiments that it is recommending that the scientist performs. So this is, again, the overall layout. The prompt is provided to the agent. It makes use of its tools and the LLM, and then provides the result, which is then sent to the lab where the experiment is performed. All right, so let me show you how this actually works. So we made use of real experimental data to test out this agent. So what does this data look like? On the right here, you see a scatter plot of the data from a genome-wide perturbation screen performed in 2 different donors, shown here on the 2 axes. Each dot here corresponds to a specific perturbation or a specific experiment. And you can see that in red here and in blue are what we call hits, or the significant phenotypes that we're looking for. In gray, we have the uninformative or not very interesting effects of perturbation. So here we have an overall roughly 18 to 19,000 genes that were perturbed, out of which 300, shown here in red and blue, are the ones that we're interested in being able to identify. So this is the data that we had. So we hid this data, and then we prompted the model to begin to predict what we should perturb. So in every round, it predicts the genes that it should be perturbing, and then we look at the actual experimental data to tell the model how many it got right and how many were not successful. And so this happens iteratively. And so here's what the result looks like. On the y-axis here, what you see is the hit ratio, or this is another term for recall, or the success rate. In every round, the agent will send its prediction to the lab, or the virtual lab. We will see what the result of those predictions are. Are they successful or not? We provide that feedback back to the model. And the model uses that information to then make another round of predictions. And so this process proceeds over and over. And then we can see over multiple rounds, the model's predictions begin to show a steady improvement in the number of hits that are being detected. We also compare this to Bayesian optimization methods. So traditionally, this field of experiment design has been dominated by Bayesian optimization. And so we tested out a number of those baselines and found that our method outperforms across multiple data sets. One of these baselines is also random selection. So just randomly picking genes also does not perform as well as our approach. And over here, you can see results across many different data sets. In black here is biodiscovery agent, or the agent we developed. And in the colored lines correspond to different baselines. So across 6 different data sets, across cell types, diseases, and different readouts, we are able to see an improvement in performance. What's most interesting is that this agent was never trained. So it's entirely used in a zero-shot setting. All you do is provide a prompt, compared to these other models that are specifically trained for this task. And so really, it leaves a lot of avenues for further improvement of these results, because there's a lot more we can potentially incorporate into the model to help it perform even better. But then a question that we often get is, how much is the agent relying on its prior knowledge versus how much is it actually using the evidence that it's getting from these experiments? So again, this is the same plot. On the y-axis is the success rate or the hit ratio. On the x-axis are the number of experimental rounds that have been performed. The black line corresponds to a random prediction. In red, we see what happens when the agent is only provided the prompt and not provided observations. And in the purple, we see what happens when you're only provided observations and no sort of biological context. And so very intuitively, we see that if you only provide the prompt, the model does very well early on because it has a good understanding of what the biology is. But then after a while, it begins to underperform the method that has access to observations, which is what you would expect in standard kind of even Bayesian formulations, where the prior stops being helpful later on, but it's more helpful early on. But what's most encouraging is if you look at the green line, where you're combining both the prompt and the observations, it consistently outperforms either of those independently. And so what this shows you is that the agent actually does have the ability to weigh both pieces of information, both its prior knowledge of biology as well as the evidence that it's gathering through these successive rounds of experiments. All right, there's also been a lot of great work around further augmenting agents using tools. So we also explored some of these. We looked at adding further reliability and interpretability to these models using a literature search. We added access to non-text-based sources, such as tabular data sets. And we also made use of an AI critic to further add another agent to this, to add another LLM to the agent, which has a different prompting strategy to see how that combines with the original LLM to produce a better output. And overall, we find that tool use does help. It is able to improve performance, particularly with LLMs that are smaller or have a lower price per token. Over here, you can see the performance across multiple different data sets. When you see in the no tool setting compared to settings with various different tools, you can see that adding all tools together is consistently improving the performance of the model on the same metric we defined before. Another interesting insight we had in the paper was this improvement of the model based on tool use is actually not something that's consistent, and it seems to correlate with the price per token of each of those different AI models. This was something a little unexpected, but also maybe intuitive, where like models that have a higher price per token probably already have a lot of the information that we get from tool use within their training. They've already sort of incorporated it through their training, and so they're probably not benefiting as much from tools as much as smaller models that have lower prices per token. And so this is something that we observe and leaves further avenue for exploration for how do we effectively develop tools that can be used with larger models as well as they can be used for smaller ones. All right, so there's more results in the paper, but I'd just like to conclude here by saying that the agent that we developed, BioDiscovery Agent, shows that we can design new experiments without training a machine learning model or even without designing an acquisition function, just by using LLMs combined with a suite of tools. These agents are very interpretable at every stage. They represent an accessible new paradigm in the computational design of biological experiments. And for future work, we're really excited to more strategically design and select tools to further augment their performance. So stay tuned for future work where we are exploring building a formal operating system for our agents, which will allow us to build a software infrastructure that connects a variety of different biological tools to agents to really kind of maximize their capabilities. And this is joint work with Cushion and other collaborators. All right, so I just want to step back a little bit to the original premise of the talk, which is really AI is impacting biological discovery in many ways, and I kind of define how these two core directions that we're observing are AI being applied towards the task of like representing biology meaningfully, as well as AI being leveraged for designing biological experiments. So at ARC, we are particularly interested in both of these directions. We are very interested especially in identifying optimal perturbations to engineer cell state and actively guide experiments in a closed loop. So as part of our virtual cell initiative, we have already developed a 7 billion parameter open source biological sequence model for DNA sequences, which is online, and it's known as EVO. And we also have a very large infrastructure set up for performing large-scale genetic perturbation experiments to really kind of bring in that data generation aspect to AI models. And so both of these combined are part of what we call our virtual cell project. And the ARC Virtual Cell Initiative's final goal is to really be able to build a model of dynamic human cell states that eventually will allow us to really just kind of click and drag cells between different states and allow the AI model to propose experiments that would optimally take us from our desired source state to our target state. So I'll end there. Thank you so much to all my collaborators, especially those at Stanford, Andrew, Chan, and Jian, who worked with me on the Biodiscovery Agent project, all the collaborators in the SNAP group, as well as collaborators at the ARC Institute. We are hiring at ARC at all levels, including my group is hiring machine learning scientists, but we also have positions for engineers. So please feel free to reach out directly or apply directly. So thank you.
Thank you. Thank you, Yusuf. Time for one question. Rishi?
Five out of six of them, you're basically state of the art, or like you're crushing them. But I noticed for Carnival too, as experiment rounds go up, some of the other techniques seem to outdo you. Do you have an intuition on why that is?
Yeah, no, that's a great question. I think what we find is for diseases and areas that are, I think, less well studied, the model has, I believe, a harder time in like outperforming. And I think what we're excited about is leveraging tools to go beyond the literature, because I believe, like, for instance, many of these data sets look at cancer, which is very overrepresented in the literature. And so we want to be able to like leverage tools to go beyond just the literature to augment this performance further. But yeah, I think there's a correlation with how well these are represented. However, I do also want to mention that not all, some of these data sets are also unpublished. So one of them in particular over here, the best performing, interestingly, is totally unpublished work. One of our collaborators generated that data. So it's not to say that it's entirely relying on the literature, but there is a little bit of a bias there, yeah.
Okay, thank you so much, Yusuf.
Okay.
Great. Another faulty laptop? No.
Let's see. I see.
Okay, super. So the last talk of this session before lunch will be by Marcel, who is a PhD student in the CS department at Stanford, and he'll talk about some lessons learned from training large-scale biological foundation models.
All right, can you hear me fine? Okay, so my talk is about what we've learned from training pretty large models. This scale basically goes up to training 100 billion parameter models. I'll get to a bit like what our model is and sort of what tricks are necessary to get something training at that scale. Yeah. So quick background, the model we're training we call Dogma LM. It's a multimodal genomic sequence model, meaning it can process currently protein and RNA, and the goal is also to process DNA with it, with the same model. The model scales that we've designed for are up to 100 billion parameters, and we've introduced some new capabilities in terms of both machine learning and the scientific side for biology compared to existing models. We've trained this on a cluster of what is currently 256 GPUs. The plan has been to increase this to 1,000 GPUs for the final runs that we want to run. Yeah, and this is work with the Chan Zuckerberg initiative. I don't think we could afford this many GPUs ourselves, so yeah, pretty happy about that. Yeah, so briefly I want to talk about what do you have to do differently when working on high-end GPUs? So at data center scale, things work a bit differently. The sort of properties of your GPUs are a bit different in ways that are relevant. So notably, compute scaling has really outpaced memory bandwidth scaling. So if you look at the different generations, so V100 is roughly like 2020-ish, A100 is like 2022, or 2021, 2022, and H100 is sort of what people are currently using, came out in like 2023. So you can see that the compute has scaled quite a lot. In particular, like between the A100 generation and the H100 generation, we have had a tripling in compute, and yet the memory bandwidth has not kept up with that. And so a lot of operations sort of behaves kind of poorly if you use the exact same process as you would on an A100. So things that you might not need to think about on the A100 scale are very different for H100s. So in particular, for any operation, memory access patterns matter a lot more. And in order to deal with that, you have some new primitives on H100s, which are sort of to do with the memory locality, and handling these in your code is something that's really, really important. So PyTorch, to some extent, can do this for you, but using it to the utmost extent at least up until quite recently, has taken a lot of work to do. And this requires going down to CUDA or Triton programming to get right. Yeah. So one thing that I like to advocate for is before you do any optimizations, you need to measure what's going on your GPUs. So key thing to notice is that very subtle changes in your design can have a huge effect on performance. And in order to see this, you need to profile your code and look at sort of which parts of the code are taking a lot of time and yeah, what you can do about them. So a great tool for this is the PyTorch profiler. There's also on the bottom left there, you can see the PyTorch memviz view. You can see there's certain operations here that really spike the memory usage very high. And you can design sort of ways of doing your computations that reduce the memory usage and increase compute, or vice versa. And sometimes you can do kill two birds with one stone. You can do them both at one time. And another thing to notice that I think is really important, a lot of people look at their GPU utilization and they think, hey, my code is great, it has 100% utilization. That's actually completely meaningless. All that means is that your CPU is waiting for your GPU. It says nothing about what the GPU is doing in the first place. So it's important to look at other metrics. You can obviously build a profile, but if you want just a rough estimate, you can actually look at the wattage of your GPU, try to understand sort of how much of the chip is being utilized from that. So wattage is actually a pretty good metric of like just pure utilization. Yeah, and so a principle that I tend to hold to is sort of these 3 points, which is first non-pessimization. So what does that mean? Don't go and optimize your code, just don't write bad code. If you can avoid doing something that is unnecessarily wasteful, do that, right? Then once you have decent non-pessimized code, then you can start measuring, and finally you can optimize for whatever you need. And it's really important to measure, because otherwise you can end up making big mistakes. So an example of that is if you want to move from sort of, nowadays I guess this is higher precision, but bfloat 16 to FP8, actually it's not as straightforward as you might think. It's not just a pure win. And in fact, at smaller sizes, I mean, even the smaller sizes here are quite large, you actually get a worsening of performance. And so for a lot of our test modules, it would not have made any sense for us to implement FP8. We're doing like sort of developments, whereas at the largest scale, at the very end when we want to deploy, FP8 might make sense in order to increase performance. So keep in mind that like for a lot of these things, they are measured by someone else, but you should definitely measure like where are your bottlenecks and try to figure out what benefits can you get from the changes that you might want to make, and sort of will that be worth it. So I want to briefly talk a little bit about what it looks like programming for H100s. So a really big part of it is thinking, how can I reduce memory costs? So as we talked about earlier, the compute is scaled a lot faster than the memory bandwidth. And what that means in practice is that you need to look for parts of your code where you can reduce the amount of memory that you need to access, or improve the memory access patterns in ways that are beneficial to your runs. So what that looks like is understanding the cache hierarchy of your machine and understanding what accesses the GPU needs to do in order to perform whatever operation you want to use. In large part, you can sort of, you can do this with pure CUDA, you can try to do optimizations in terms of like memory layout with PyTorch, but the best possible performance you get if you use an actual compiler that goes down to the CUDA level and can optimize every little part of it. And I'll talk a bit about Triton, which is the sort of sweet spot, I think, of easy to use and optimal on hardware. And for like a reference, a lot of the operations are between 3 and 15 times faster when you do compilation and fusion. And often you can even completely eliminate the memory usage of your kernel in the first place, which is really nice, depending on what the operation is. So I want to show a very brief example of sort of the meat of what a Triton function looks like. So importantly, it's written in Python, and you sort of use the Triton compiler, which is a Python library, to compile this. It's actually included with PyTorch. So if you install PyTorch, you already have Triton. You write a few pieces of code that tell Triton what the blocks should look like, so what the access pattern should look like on the GPU, or on the individual tensors that you load on the GPU. You can see sort of on the right there, I have a diagram of what this sort of access pattern would look like at the very end. And importantly here, we use blocks as our fundamental units. Then afterwards, you do your operations. So you can see we have a loop here. Importantly, this loop will be compiled, which you should never loop like this in Python, but you can in Triton. And you can load the memory you need, do the operations. You can see it's very simple. You just add it to an accumulator. And then finally, you advance your pointers. And then at the very end, you want to write out your results. So you have block pointers that point to different parts in memory. Depending on sort of which thread is acting currently, you can write to different parts in memory. Yeah. So that was just a brief aside about H100 programming. I don't want to go too in-depth here, but I really recommend looking at the Triton documentation and the tutorials if you're interested in sort of seeing the power of this and sort of how much you can get from these very simple kernels that you can write that have a big impact. So moving on, I want to talk a bit about sort of the machine learning side of our model and what was needed basically to get the performance levels that we're currently at for embeddings. So there are two sort of standard ways of doing machine learning on text or on sequences more generally. One of them is to do BERT masking and to learn with full attention on a BERT masked input. So what that means is you hide individual inputs. I don't know. Never mind. So if you look at the BERT window, you can see that there's one token there is masked, and all tokens are attending to all other tokens, and they're trying to predict what are the masked tokens at the very end. Some pros of this are that you have usually much better embeddings than the alternative. This is because sort of every token is contributing to predicting every other token. So when you're looking at the individual masked tokens, you have to sort of use all the information you possibly have, and then like every other token also needs to contribute to being able to predict the masked tokens. So that means that like you're actually using all the information all the time. There's no like kind of drop off. We'll talk a bit later about what the alternative is, or I'll talk about that in a second. But yeah, that's a big pro. And yeah, you actually pay full attention to the visible tokens. So con of this is that if I mask a certain set of tokens, I'm learning what it's like to predict that exact size of masked tokens. So if you fix your masking percentage, say you have 15% masking, you're learning what it's like to predict 15% masked input. And so if you input then a sequence that is not masked at all, which is what you usually want to do when you produce embeddings, you sort of have never seen that example in the wild. And you don't necessarily, usually you have pretty decent embeddings, but that's not a necessity. Like it's not something that's being trained for explicitly. So the alternative is to use GPT, and GPT is about always predicting the next token based on the information from all the previous tokens. So an issue here, a big benefit of this is that you're learning from every single token. So you get learning signals from every token that you see, and it's used to train the representations for what you've already seen previously. This also lets you have a generative capability. So you have this generalization ability where if I see 5 tokens, I can predict the 6th one. If I see 100 tokens, I can predict the 101st one, which is something that BERT severely lacks, because in BERT you have to specify a specific masking percentage. Oops, sorry. And a big con of this is you can only see tokens from one side. So what does that mean? If I go through my, so if I have a biological sequence, I care about what's happening before and after the token that I'm predicting. And with BERT, I can do that. With BERT, I can mask a token that's in the middle of everything, and I can see what's happening all around this token, this specific element, and understand what's happening in the sequence from that. With GPT, I'm only predicting the next token. And so really what's relevant is what's close to me in the first place, and it's only being used to predict the next token. So really, information does not need to pass from the current token to the next token in order to, like, for predicting a token that's 20 tokens forward in time, because there's not really that like level of interaction happening, especially at early layers in the model. So what we propose is combining GPT and BERT together. And so the idea here is, well, what if we select the masked tokens that we had? So say in the top left here, we have an example where we've masked out tokens 2 and 4, and we move them to the end of the sequence, and then we use this as a GPT sample. So what the model is seeing now when it's going through and predicting next token, so say the next token prediction starts after token 5, is it tries to fill in what the index 2 is. So one thing to bring up importantly here is that you have to also move the positional indices. So when you move the positional indices, and thus the positional embeddings, you have an understanding of sort of where it is in the sequence, yet it's causally next in the sequence, despite it being at the very end, despite it being in the middle of the sequence that you're predicting, right? So you basically have a blank, you try to fill that in, and now when you try to predict the next token, you have that filled in, you have it causally present for predicting the next token. And so you sort of effectively have a variable masking, where at every level you're not only predicting a token, but adding it to the set of tokens that you can now use to predict the rest of the tokens. So importantly here, we expect embedding quality to be really high, because you need to, the sequence needs to be ready to predict any missing token, not just the next token in the sequence, right? And so you don't have this like local problem where in GPT, all that really matters is the next token, and you can sort of forget everything about what's happened in the past, unless it's directly relevant for predicting the next token. And you can greatly increase the masking percentage for more learned tokens. So that means like if I now increase my masking percentage to 40% or something, I will eventually get to the point where I'm 15% masked, which is what you would usually do in the BERT case. But you also have the higher masking percentage represented and the lower masking percentage represented in the same sequence. And that also means, you can use more information, as you predict the later elements in the sequence. So further, this means that you get better generality, right? So, and you can have generative capabilities. So if I predict one element of the sequence, I can now use that to predict the next element of the sequence. It will be conditional on what you've already seen. So this adds more capabilities as well as sort of improving the embedding quality. So further, moving a bit more away from the machine learning side of things, I want to talk about the data processing side of things. So a big problem that we had early on in our training setup was the data sets are really large for proteins specifically, but also for other data modalities. And a huge problem here is that the data itself has highly variable lengths. And very often you want to do this like random lookup in your data set. So you want to get a specific sequence because it's related to another sequence in a way that sort of doesn't really show up in text-based models very often. So what we built is this way, first of all, of packing tokens together. I mean, this existed somewhat obviously, but basically instead of having padding, so instead of organizing things in terms of a tensor, we pack them together in a representation that also allows us to have random access because we store the indices sort of the boundaries between the tokens. This is at the far right here of the example. Sorry, keep doing that. Oops. Yeah, so because of this representation, we can now use a lot of the tools that exist in Python, but some of the operations are sort of very specific to biology and specific to these kinds of sequences in the first place, and need to be implemented in some other fast language, because iterating through it in Python it takes like literal days to get through. So we have some Rust operations that we've implemented some operations in Rust that we can call from Python to run perfectly in parallel, yet be completely controlled from Python. So we can have our data organized in Python, but use Rust operations to sort of do operations on them. And all this can be done in parallel, like perfectly in parallel. So the combination of using multi-core, compiling your operations with Rust, this representation obviously, but also having a fast compression algorithm, gives us around 1,000 times speed up for data processing. So that means that we can easily experiment with this, because you can go from more than a day of computation to around a minute of computation for reprocessing your data set. And that means that we can test our data hypothesis very quickly. So a big problem here is that in biology, when you change your data set, sort of like you still need the random accesses, you still need the indices built, all this stuff, right? That takes up a lot of, that you need to recompute every single time. And if you mix data sets, there's metadata that needs to be added. A lot of things need to go right here. So the sort of mix of having fast operations and having the flexibility of using them from Python gives us a huge boost in terms of the productivity for data processing. Yeah. So I want to also talk about what happens to models as you scale them up. So if you trained medium-sized models, you've sort of seen a lot of different behaviors. You've seen things converge, diverge, probably. You've seen, certain architecture decisions matter a lot, others not so much maybe. But in the large scale, things act a bit differently. So importantly, any small instability that might have been fine in your small model ends up being crucial to the training of your large model. And you could end up having a situation such as this graph at the right. Here, the precision of a single operation in the normalization implementation was, bfloat 16 instead of floating point 32. And at a random time, just towards the end of training, it just spikes up immediately. You need to really scrutinize the precision of specific operations a lot. A good way of getting this right often is using library functions, but often you want to experiment with things that there are no libraries for. You need to be very careful about how you implement things. So in particular, with larger scale models, you often end up accumulating over a larger dimension. And accumulation is an operation that sort of compounds inaccuracies in a way that's not great. And so it's very important to use high precision when you're doing accumulation operations. And this also translates to writing your kernels in Triton or whatever. You need to be very careful about what precision you use at what points of the computation. Yeah. And so once you get this right, I think an interesting consequence is that once you have scale and stability, you get a highly predictable model that you can know where it's going to end up after a certain amount of training. It's often easy to tell which models are good, even after less than one epoch. You can sort of see the comparison lines for training and understand better, quite well, what the final result is going to be, even before you've seen the full amount of training, right? Yeah, and it turns out in this setting also, exact details of the optimizer parameters and groups matter a lot. For instance, one thing that we discovered, a few months into training is that there's specific terms that you should never have weight decay for. So if you weight decay your bias terms, stop doing that. Yeah, and so another issue that shows up that was sort of brought up in the Llama 3.1 paper is this issue of error rates. So you can expect roughly one GPU failure per day per 1,000 H100 GPUs, right? What that means is, if you're using 256 GPUs, you expect a failure roughly every 4 days. So if you have a long-running training run, you got to make sure you handle, actual crashes. It doesn't have to be your fault at all. The GPU is doing so many computations that something is bound to fail. And really, it turns out that frequent checkpointing is the only reliable solution, but it's sometimes quite hard to get the checkpointing right. And importantly, you need it to be, not too disturbing to the training runs that you're doing. You want the resumptions to be exact. So if I have a bad data sample, I would like to go back and rerun this and, start from the exact point in the data loader so I can find the exact data sample that caused some spike in the loss. Or, if it's random noise, I want to be able to resume and, understand that that's actually what happened. It was some, cosmic ray that bumped my GPU off the right track. Yeah. So also one thing to note is that resumption with a different number of GPUs than what you trained on is not trivial. And yeah, it's something you should think about early on when designing your model. Yeah, so time's almost up here. I want to briefly recommend some tools. So this is as of November 2024. Interestingly, sort of two of these did not exist when I started, back in my day of February 2024. The world looked very different. And now we have these PyTorch native developed libraries, which are Torch Titan and Torch Tune. So this sort of trend has been to take these libraries that have been very successful and standardize them within PyTorch. And so now I would say use the attention mechanism that exists in PyTorch 2.5. Before that, you'd have to use some external implementation. That was a real pain to work with. I'm sure people in this room have used it before. You should also use Triton directly. You can use Torch Compile to get around a lot of the H100 specific optimizations that I talked about, but using Triton directly gives you more control, and especially for memory efficiency, it's really, really useful to have Triton access. So Torch Titan is a good tool to scale things up and shard models. So if you need to split models across several GPUs or across an entire cluster, a lot of the sort of operations are made much simpler in Torch Titan than what they were in the tools that were available in February, for instance. And additionally, if you get to insane scale, you can start using FP8, which is also included in sort of this Torch Titan sub module. Yeah, and finally, Torch Tune is a good library for loading these checkpoints. If you use Torch Titan, you can use Torch Tune to load these checkpoints and do further operations with them in a way that's still not slow, like actually quite useful. And yeah, this is, I think, a good set of sort of starting points for what to use. And actually, I don't think you need much more than this to do mostly anything you'd like to do in large language model training, at least. So yeah, finally, have some acknowledgements. These are my collaborators. Yeah, thank you so much.
Okay, the light is back. Thank you, Marcel. Maybe a question? Yeah, and then food.
Oh, thanks for the talk. So I think I imagine like the DNA and RNA sequences have a lot of repeats and stuff, so it's different from normal text. So the GPT-style decoder model might suffer from like exposure bias. And I've seen like prior work that use like random spam masking to reduce the exposure bias. But your framework is very interesting, like the GPT plus BERT, and then you seem to be doing that masking already. So in your experiment, do you see any like reduction of exposure bias, or is this still a problem?
So we've dealt with that mostly through the data preprocessing. We have a clustering setup that allows us to group sequences that are similar together. And so we sort of sample them in a smart way to be representative of the entire space rather than the individual sequences. I think that's the main way we've dealt with it. So we've sort of always had a way of dealing with this. We haven't noticed any difference in that specific problem, though. But I think, I don't think we've played enough with the generative aspect of the model yet, which would be interesting, I think. And maybe we can look into that.
Thank you, yeah.
Awesome. One more?
Another question?
So as you combine BERT and GPT, so your position for the token that you are going to predict have changed. Does that increase the sparsity of the model, and does that make you optimizing your model more challenging in any ways?
No, actually. So it works out very neatly if you look at the math. Sort of, we've laid it out, and all you need to do is you need to change sort of what positional indices you give to the queries versus the keys. So a key problem here is like a query is asking for the next token, not its own position, right? So you need to shift these over by one, basically, to ask for like where the next token is going to be. Because in a standard GPT model, you have like the positional index is only your own, whereas in our case the keys will be your own positional index, but the queries will be a different positional index. It doesn't change the sparsity pattern, as far as I know. Like you can actually just use a totally standard GPT implementation. It'll work very straightforwardly. Yeah.
Awesome. Thank you so much. So we have a lunch break and we continue at 1:30 p.m. Thanks a lot. great.
It works.
Amazing.
It's set up.
It's a good setup. Okay.
So
We'll wait a minute or two.
sure. Very good turnout.
Yeah, we invite. Yeah, this year is very.
Hello? So it's my pleasure to introduce the next speaker, which is my friend Vasilis Ioannidis. He's a research scientist at Amazon, senior research scientist at Amazon, and he will talk about enhancing large language model reasoning with structured data. So, Vasily, the floor is yours.
Thank you, my friend. So thank you for the invitation today. And today I will discuss about how we are using large language models and specifically enhancing them with structured data across 3 different directions. So the first direction I will discuss about is how we can use graph foundational models, that is actually a superposition of language models and GNNs. And the second direction is how can we use knowledge graphs to specifically supervise large language models. And the third final direction is GraphRag, which I'm pretty sure you know that is very heavily abused word, but I will try to give you a specific interpretation of how we are using RAG with structure to complement language models with graph context. So this work, the language model GNN, is something we started 2 years ago, or 3 years ago. And this essentially talks about how can you efficiently and effectively train the superposition of language and graph neural network models. So the motivation behind that is you have a lot of applications, but specifically in shopping, which is something any e-commerce company is interested in, where you have multiple entities, right? So you have like buyers, products, sellers, and you also have, for example, queries. And all of these kind of different entities are actually associated with rich textual semantics, right? And this rich textual semantics here can be utilized in order to get a more advanced representation, improved representation. Overall, what we have in the end is a multi-entity heterogeneous graph with rich textual features. And in this first presentation, I want to highlight the language model GNN framework or architecture. And in fact, as you can see, it has 2 main components. The language modeling component, which is, for example, a transformer model, or you can imagine a large language model there as well. And then the second component, which is the GNN encoder. And the flow is that the text passes through the LLM and gets embedded into a vector, and then this vector is fed to a GNN encoder that will combine all of the embeddings that come from the various kind of source nodes. And this is end-to-end supervised using a link prediction loss. But the key question here is how do you do this end-to-end backpropagation algorithm, right? So it is not that obvious as maybe it seems. So there are a lot of challenges first related to the efficiency of this method. So specifically, you can imagine you have the two-hop neighborhood explosion, commonly known, right? So for example, I follow Jure, and Jure is followed by hundreds of millions of other people. So then the two-hopping network of me, just because I'm following Jure Leskovec, then it becomes very, very expensive, right? Of course, there are a lot of methods in the GNN literature that people have used to minimize this number of nodes. And in fact, random sampling of your neighborhoods has shown to be actually very, very good approximation. So, but let's say that you only have 400, a conservative estimate, that in the two-hopping network, I only have 400 nodes. This still means that in this composite architecture, you need to do 400 passes through the language model in the backpropagation algorithm for a single target node. And how many target nodes do we have? Well, in graphs that are trillions of edges, you have hundreds of billions of target nodes. So then you can understand that you need to actually have very smart mechanisms of optimization to optimize this thing. And specifically what we do is we try to distribute the graph, and we partition the graph across machines and across GPUs, so you have multiple levels of partitioning of the graph. And then within each partition, we are trying to actually, again, furthermore optimize by using smart caching algorithms to cache the embeddings and do not backpropagate always the loss. So the second, actually, set of challenges relates to effectiveness. And effectiveness practically has to do with how can you make this work, like even end-to-end training of this model will not work out of the box. The reason is that these language models are heavily trained for text data, and they cannot understand very well graph data. So you need to do some kind of stage-wise fine-tuning, which is what we propose in this paper. And overall, the three-stage fine-tuning achieves the best performance across link prediction and node prediction tasks for these text-heavy graphs. And finally, I wanted to mention that this LMGNN architecture is available for, is open sourced in the GraphStorm package that later we will have also a poster that Xiang will present, which will be discussing about GraphStorm and all of the models they are provided there. So now I want to go one step deeper onto the research that we did on this LMGNN architecture. Specifically, the problem we are trying to solve here is given a large corpus, which means a graph that can be an e-commerce graph that can be very large and accommodating a lot of different applications, can we actually pre-train the model, the LMGNN model, once on this large graph and utilize it on many different applications? And what you can see here is how this large graph corpus looks like. You have queries, you have products, and you have different relationships among these entities. And you also have many downstream tasks that can be mapped to this actually large graph corpus. So you, based on a query, what is the most probable product you need to show to the page for the customer to click it? So this is one task. And what we show in this work, you can read more by following the link, is that you can actually indeed pre-train the large language model GNN once on this large graph and utilize it on many downstream graphs. And this can help you avoid retraining in every different application graph every time. So this was like maybe the first component of the talk, which was discussing more about the foundational models. In the second part of the talk, we'll discuss how can we use actually domain-specific knowledge graphs in order to enhance performance of language models. And knowledge graphs applications have been around for a very long time. So people have actually created a lot of specialized knowledge graphs in a lot of different domains. We also discussed earlier about different knowledge graphs that are used in biology, right? And the purpose of this work was how can we utilize actually these knowledge graphs in order to actually bring multimodality in biomedical foundational models. And what we actually specifically do here is you can imagine you have multiple entities like disease, drug, protein, and biological processes. And then, essentially, these different entities are encoded by different foundational models. But we know, in fact, that these entities are related through a knowledge graph, through biological knowledge graphs. So now the question is, can you actually supervise these foundational models through these knowledge graphs and align them to some extent by tracking these relationships and optimizing on these relationships? And this is what we do in this ISLR paper. And you can find that actually these kind of models perform very well on a variety of tasks that they have not specifically been optimized for, because of course through the actually knowledge that is encoded in the knowledge graph, if you capture this knowledge well, you can do well on these tasks. So this is what we saw actually in this paper, in this work. And now I want to move to the last part of this presentation, which goes to GraphRag. And again, I want to recap that GraphRag has been heavily abused by in different ways, but the way we are trying to describe it here is, can you effectively use structure among data to improve RAG systems? And in fact, in this collaboration, we did a lot of work with the Stanford team, as you will see soon. So let me first describe in a very high level retrieval augmented generations for the uninitiated. So the RAG systems unlock a new set of capabilities of LLMs, specifically when you require access to up-to-date data or private data sources. These are data sources where the LLM has never seen on, but you want to build a QA chatbot on these data sets. So for example, you are a hospital, you want to ask questions about your patient, but of course, ChatGPT doesn't know your patients, right? So you need to provide documents that describe your patients. And typically, the process involves 3 steps. First, you chunk the data, you chunk the documents, and you embed each chunk. And then, in QA tasks, you embed the question as well, and then you try to do an approximate nearest neighbors method to find the most relevant chunks to your question chunk. And finally, the chunks and the question are provided as context to the LLM. But what is actually, what is very interesting is that in industry and across different applications, you have a collection of structured data as well on top of the unstructured data that are simply the documents. And structured data can be represented with relations, graphs, and tables. And in this case, actually, we need to actually think how can we extend RAG systems to this semi-structured knowledge bases, okay? And the main challenge here is that there is no public available reliable dataset for profiling retrieval on this kind of, or reasoning over the structured knowledge bases. So then we embarked with the Stanford group into the following project. As you can see here, there are some known faces. I'm also there, but I have a beard there. So in fact, we are trying to benchmark structured knowledge bases for QA tasks. And the way we are trying to go about this problem is, you imagine you have a user, right, that wants to ask questions over a retrieval system, but he wants to ask these questions, he or she wants to ask these questions over a semi-structured knowledge base. So a semi-structured knowledge base, as we discussed earlier, is a collection of documents, but also relationships, right? And in this case, we didn't have any such benchmark. So what we did is we collected QA pairs through participants that provide a small set of questions and answers. And the questions need to both combine data from the relations, but also features from the database in order to be answered. And we constructed such QA pairs through the participants, and then we used kind of LLMs in a synthesis way to large-scale generate QA pairs. So this provides us with a robust set of QA pairs, which can be used in order to benchmark the different QA methods. So this covers actually product search, precision medicine, but also academic search. And the queries are natural and diverse, but most importantly, this is a challenging task that is quite common in industry, and traditional retrievers fail. And this is what you can see by going through this paper, where we profile different traditional retrievers, and they perform really poorly. So actually, what does this tell you is that there is opportunity to actually invest on semi-structured retrievers that can account for both the structured and the unstructured data. So this is the next set of works we did with the Stanford team, which is the Avatar project, where actually we try to utilize agents, generalist agents, for retrieval over this kind of semi-structured knowledge bases. And the intuition here is that, that we try to solve is that agents sometimes use tools poorly in the semi-structured knowledge bases. For example, they chose wrong tools, or they perform a function call that returns an error, so probably there was some error in how the function was called, and they ignore key attributes. The reason for that is that in semi-structured knowledge bases, the task is inherently more difficult than just retrieving certain chunks. And the way we try to solve that is to use contrastive reasoning. And contrastive reasoning here has been done by a comparator module that is practically an LLM that tries to classify actions into positive actions and negative actions. So the negative actions are actions that our agent took and should not have taken because resulting to some negative kind of feedback. And the positive actions are successful, let's say, actions that should have been done. And this actually implements a contrastive reasoning framework that can train actually the agent into a self-improvement function. So what you see here in these graphs is that we see that as the iterations grow, the agentic performance actually of the model increases as well over time, because actually Avatar learns how to improve tool usage by self-reflection and achieves SOTA results for structured knowledge bases. Overall, here we achieved reduced hallucination rate with grounded knowledge, and we actually achieved trustworthy decision-making with interpretable actions, because right now our actions are grounded on this semi-structured knowledge base. So we can track back and see why this action was made by following, for example, the relationships. So this was actually a major work that I think potentially can have benefit across other domains as well, but specifically for semi-structured knowledge bases. So in the last few months with our research group, we also tried to extend parts of this work where we try to improve retrieval over semi-structured knowledge bases. But specifically, we try to utilize these two intuitions. The first one is that you do not always need information from both modalities. So sometimes your answer can be entirely answerable by the structured data, or it can be answerable by the actually unstructured data. And this was kind of the first intuition. And the second intuition is, instead of actually using the agent to search over a variety of tools, can we make more specialized tools and use them actually for retrieval? So this is the agent G actually work, what we did. And specifically, we introduce a selector module that will decide which retriever bank to use. Will it use the graph retriever bank or actually the text retriever bank? And we developed an unsupervised graph retriever that works well across kind of cases. So it's not trained for the specific use case, but it actually is an architecture that can work well across graph retriever setups. And we introduced a critic actually to filter the answers. And practically there is a decision layer that decides, is your answer good enough to be presented as an answer, or you should improve your answer. So by introducing these three components, we achieved some improvements over the previously mentioned method. So I want to finalize with some conclusions and leave some time for actually questions. So today we discussed about foundational graph language models and the LMGNN architecture. And I also talked to you a little bit about pre-training on a very large graph corpus and specializing the model on different applications. And then I also show you some of our ongoing work, which is using knowledge graphs to improve RAG, constructing efficient and effective knowledge graph from data sources, which is something else we are also working on. I didn't have time to discuss it today. And also how you utilize this structured data for retrieval, which is actually part of what we call GraphRAG. And some of this work will be soon available in AWS as different products, so you can reach out to us if you are interested. So thank you for your attention and for the invitation as well.
Do you have any questions?
For the LM-GNN architecture,
Right.
have you kind of benchmarked or compared it against like traditional foundation models trained on the same corpus? I'm curious, like, how big of a lift do you see?
That's a very good question. So the question was, for example, for this text graph, have you profiled specifically foundational models that do not account for any graph information, and how do they perform? So in fact, they perform like very well as well, but we see something like a 5% improvement when we utilize our actually graph-aware fine-tuning, if you want. And you can see actually more in that paper. I don't have here the numbers, but you can see a performance increase across node prediction and link prediction. I would say, of course, in link prediction, it's much more important to utilize the structure, whereas in node prediction, in some cases, text can be very indicative of the downstream label, so maybe you see a smaller gain.
Yeah, that makes sense. Thank you.
Yes. Yeah.
Hi there. Yeah, the Stark data sets, by the way, are very helpful for us, so thank you very much for that. I had a question more about evaluation, because in industry, especially with natural language responses, it's not always like this node is the right answer, right? It could be a combination of nodes. Sometimes there's multiple right answers. So is there any thought for future work about like the evaluation frameworks and the objective functions that are used for that in terms of baselining these different techniques?
Yeah. So I think that's a great question. So the question was about evaluation mechanisms in the GraphRag world or in general in the QA world. I believe this is a very, very important topic that is very, very underfunded. The reason is that everyone cares about new features, but not so much about better evaluation methods. Anyway, so I think yes. So we are actually following two ways to go about that. So the first way is to try to utilize some kind of human in the loop in order to kind of fine-tune the synthetic data generation process, which provides us more data, right? And the other way we go about this is to use actually LLMs as judges. And the LLMs as judges practically is an external LLM that will evaluate how good you do, for example, on these tasks, and tell you, oh, this question answers, this answer answers well that question. This means what happens when you have questions without an answer, right? So because you don't always have QA pairs. In some cases, you only have queues. You only have questions. Right. So I think these are the two threads that we are following in that aspect. Yeah. Thank you.
Okay. Thank you, Vasily.
Thank you. Thank you.
Super. So next talk, Harilaos Kanatsoulis. He's a research scientist at Stanford in the computer science department. And Harilaos is doing very interesting work on how to extend transformers to graphical data, and especially thinking very deeply about positional and structural encodings in them.
Thank you, thank you. So hi everyone. What happened? Okay. So I'm super happy to be around you today and discuss about a topic I have been working over the past year, and this is next generation graph transformers. Oops. Oh. So this is a joint work with some amazing collaborators. Of course, Jure and Evelyn from Stanford, and Stephanie and Alejandro from MIT and the University of Pennsylvania. Now, over the past few years, we have observed an unprecedented success of deep learning models, of deep learning methods, especially when it comes to processing data that are of the form of a sequence or of the form of a grid. So previously, Vasilis and Rishi emphasized on the power and the success of large language models in processing and manipulating text, or more generally, natural language. And I think Yanai will later discuss the power and the success of large models in learning from biological sequences. And of course, we have all observed the success of computer vision and image processing tools or image processing methods, especially with a large amount of data. Now, a fundamental component of the success of these deep learning models is without the doubt the transformer architecture, which is, as you can see, illustrated in this super famous diagram. As you can see, the transformer architecture consists of several parts, and arguably those that drive most of the performance are two. One is the self-attention, which is a form of a nonlinear projection, or if you like, a form of a nonlinear convolution, and the positional encoding, which, as the word says, it encodes the position of each token in the sequence when we talk about text, and the position of each token in the grid when we talk about images. Now, long story short, the transformer is an amazing tool, and graph aficionados as myself, and I believe many of you here, are very interested in somehow leveraging the power of the transformer in doing machine learning and deep learning on graphs. However, when it comes to processing or learning with graphs, things become very tricky. And there are many reasons behind that. One of them is that graphs usually have multiple and diverse modalities of information. So they have at least two. They have information at the entity level and information at the graph level, which is the graph structure. For example, in a social network, we have the images and the text at the user profiles, and also the connectivity information between different users. So we know who is friends with whom. And also, if we look at molecular graphs, we have the type of atoms or functional groups, which is the entity-level information, the entity-level signal, and we have the bonds between different atoms, or the bonds between different functional groups. So on the one hand, we have the entity-level information, which is usually text. It is an image or a categorical variable, and we know how to effectively process and learn from them. And on the other hand, we have the graph structure, which processing it becomes very challenging. So the goal here is to jointly process these two modalities of information, the entity-level signal, but more importantly, the graph structure using a transformer. So in order to understand how we can do that, let's take a step back and observe or somehow look deeper into the hidden structure of sequences and images. To be more precise, let's look at this sentence here. The cat ate sushi, whatever that means. And if we consider, or if we think of a sentence as a sequence of tokens, it is easy to see that this sentence has actually a hidden graph structure, which is the line graph. Long story short, each token is connected to the previous token. So what happens to the transformer? Oops. The transformer takes the words or sub-words and represents them into tokens. And then it encodes the structure of the sentence, or in other words, the syntax, using positional encodings. So the text positional encoding encodes the order of the token in the sequence. And something similar happens when we look at images. We can consider an image as a set of pixels. And if we do so, we will see that this pixel have a hidden graph structure, and this is the grid graph. Again, long story short, we have pixels that are connected to nearby pixels. Now, what happens again in the transformer is that pixels are represented by tokens, and then the transformer encodes the structure of the image or the pixel position using positional encodings. In other words, image positional encodings somehow encode the position of the pixel in the two-dimensional space. Now, the point I want to make here is that the transformer architecture explicitly encodes the graph structure, which is, in that case, a very specific graph structure. It's the line graph or the grid graph using positional encodings. Now, a very natural question is that can we actually design positional encodings that effectively encode the structure not just of line graphs or grid graphs, but of arbitrary graphs, of graphs that have a very abstract or complex structure, like the graphs I show here. But we are not only interested in finding any positional encoding, we are interested in finding positional encodings that admit 4 favorable properties. Property number 1, we need them to be expressive, meaning that they should somehow encode as much information from the graph as possible. We want them to be equivariant so that they can be generalized across unseen graphs. And we want them to be generic, so not tailored to a specific domain, but applicable to multiple domains. So the final property we would like our encodings to have is to be scalable, because many encodings work very well for small molecular graphs, but we actually are in need of positional encodings that can be applied in larger graphs. And if we go back to the question, can we actually design or learn such positional encodings, the answer that admit these favorable properties, the answer is yes, and later in this presentation I will try to show you how. But before I do that, let's discuss some prior work. So researchers have studied positional encodings for a few years now, I would say 3 to 4 years, and state-of-the-art methods are using eigenvectors of the graph Laplacian as node positional encodings. So the graph, for those of you that are not very familiar, the graph Laplacian is a matrix that encodes the graph structure. It encodes local and global properties of the graph. And what happens is that the eigenvectors of the graph Laplacian somehow inherits these very nice local and global properties. Now, when a graph has n number of nodes, it usually has n distinct eigenvectors. And the number of eigenvectors we are using to somehow design these positional encodings is a design choice, but not just a design choice that somehow defines the properties of the positional encodings. To be more precise, we can have positional encodings that look at all the eigenvectors of the graph Laplacian, and these positional encodings have very high expressive power, they are generalizable, they are generic, and however, they need cubic type complexity, and they need quadratic memory complexity. Now, there is a way to overcome this limitation of the complexity limitation, and this is to compute, let's say, a subset of eigenvectors, or the top k, let's say, or the bottom k eigenvectors. And these methods work very well, and they have a approximately linear complexity. However, they work well in practice, but they have a little bit less or lower expressive power, a little bit lower generalization ability because of stability reasons, and they add some sort of inductive bias because different eigenvectors or different number of eigenvectors means different things for different graphs. Now, in the remaining of the talk, what I will do is I will propose a novel positional encoding framework that leverages the power of message-passing graph neural networks to somehow compute eigenvector-based positional encodings that have high expressive power, they have high generalization ability, they are generic, but they are, as I said, they are eigenvector-based, but they can be computed with 1 order or 2 orders of magnitude lower computational complexity. So I have 2 slides of analysis, very simple things. So Josh gave you a primer on graph neural networks. So a graph neural network layer looks like that, where x of v is the embedding of node v, and we consider the embedding of node v at layer L and at layer L minus 1. And the update for node v takes into account the update of node V at the previous layer and also the embedding of the neighbors of V. And the way they do, the way the message passing graph neural network does that is that it uses two functions. One is function F, which aggregates information from the neighboring nodes. And there is a function G that combines information from, of each vertex with the aggregated one from the neighboring signals. Now, the reason why I include this equation here is because we have a very nice observation, a very nice remark. And this remark is the fact that the graph neural network layer, the graph neural network update, can also be viewed as a nonlinear function of eigenvectors. So to be more precise, we have this update here, and this update is exactly a nonlinear function H, which can be an MLP, of the eigenvectors V. So V is the matrix of eigenvector, and this function is parameterized by the update of V at the previous layer and the update of neighbors of V. So actually, this observation is pretty cool because it implies the following. It implies that maybe there is no need to compute eigenvectors with the complexity, some complexity problems, but we can use message passing graph neural network to learn positional encodings that somehow imitate eigenvectors. So that is the idea. And this is our proposed, or the high-level, somehow illustration of our proposed Perl architecture. So what happens here is that we have the input graph that has some node attributes. So we use these node attributes as initial tokens for the graph transformer. And then what we do is we remove the node attributes and use a message passing graph neural network to only process the graph structure. Now, for those of you that are super familiar with message passing graph neural network, you might wonder the following. You might say, okay, I mean, message passing graph neural network work great, but when it comes to processing graph structure without node attributes, there are certain limitations, structural limitations, what we call WL limitations. Now, in order to overcome, and this is actually true, however, there are ways to overcome these limitations. And today I will not tell you how, or I will not tell you why, but I will tell you a way to overcome this limitation. So the way that we'll do that is that we'll somehow generate some synthetic node attributes, initial node attributes, which will break some symmetries and allow message passing to unleash the true potential, the true expressive power. But to be more precise, let's zoom in into this part of the architecture. So what happens here, is that, as I said, we have the graph that has some initial node attributes, and then we remove this node attribute, so we only have the graph structure. And then for each node in the graph, what we will do is we will associate each node with an M set of samples, M set of values. So we'll draw M samples from a probability distribution for each node. So this, for example, if we look at node 4 here, we will draw M different values. So we'll have, I don't know, let's say 0.1, 0.2, 0.3, which are these new node attributes for node 4. And we'll do the same for every node in this graph. And then each of these samples for all the nodes will be processed independently through a graph neural network to produce an output encoding, an output representation. So for each sample, we have a corresponding output. So what we have achieved here is, as I said, somehow break the symmetries using this randomness. However, there is a caveat that we somehow violate the equivariance or the generalization of the model. And there is a simple way to reconcile for that, to overcome that, and this is by using this pooling function rho here. So what we do is, again, let me recap, is that we draw random samples for each node. We pass these samples independently through a message passing graph neural network that breaks symmetries and increases expressivity, and then we use a pooling function that maintains the symmetry, but at the same time, it is expressive enough for our purposes. So to recap, this is let's say the high-level picture of our proposed Perl architecture. And it has some very interesting properties. As I said, it has high expressive power. It can compute cycles and quasi-cliques that are super important both for molecular graphs and social networks and other types of graphs. It is equivariant, which means it can generalize across new graphs. And it is generic, so it's not tailored to a specific domain. And what is super cool is that the computational memory complexity is O m times n. N is the number of nodes, m is the number of samples. And the number of samples for large graphs can be much lower than the number of nodes. So it's kind of independent from the size of the graph. So now we test our proposed approach in two tasks. One is on small molecules, and what we are doing here is we're trying to predict a specific molecular property called log P, and we are using the zinc, the famous zinc dataset for that. So in terms of a graph task, this looks like a graph regression task. And you can see here now in the y-axis we have a method that doesn't use any positional encodings, a method that uses Laplacian positional encodings, another one which is an invariant version of Laplacian positional encodings, and our proposed method which is called Perl. As you can see, our proposed method is almost, I would say, 3 times or 2 times better than methods without positional encodings, and somehow 20% better than the best competing alternative. And the next task is graph classification, which uses kind of larger data with larger graphs. So the task here is to classify social Reddit graphs according to the thread type. So in terms of a graph task, this is graph classification with 5 different classes. And as you can see, here I present the classification accuracy, higher is better. And again, we have a similar picture. We have a big benefit compared to no positional encoding, and some also very, very interesting benefit compared to the competing alternatives. And with this slide, I will conclude my talk, and I'm ready for any questions that you might have.
Hi, great talk. Thanks. Is the pooling function in a way kind of a memory of what the...
Depends. So what we are using here is summation. So you can do it online. You don't need to have a memory necessarily. Right. You need to have a memory of the current, let's say, estimate of the pooling, of the current estimate of the summation. So it's not too big of a deal.
Okay, thanks.
Yeah. So that's a great point. So because I don't think that people could hear you, the question is if we need to train the positional encoding for its dataset, or there is a, let's say, unsupervised or self-supervised way to do so. So for our current results, we train for its dataset, but there is nothing that prohibits us from training in an unsupervised link prediction manner and learn this type of embeddings or positional encodings.
Yeah. One last one. Great talk. I have a question regarding the spectral clustering thing, the spectral embeddings, positional embeddings thing. You said essentially you try to imitate the operation that the Laplacian is trying to achieve. And essentially my question is twofold. First of all, when you say imitate, do you mean in some sort of like formal kind of imitation, or essentially you just try to completely replace it with something that's more efficient and flexible without any sort of theoretical underlying connection? Yeah, actually this was the first part. And
so I don't remember if I used the word imitate, maybe it's the wrong use of the verb. So we're not exactly imitating. So what we're doing is that we first observe that a message passing graph neural network is actually a nonlinear function of eigenvectors, either of the graph adjacency or the Laplacian, depending on your somehow message function or aggregation function. And what we're saying is that there is no need to bother about imitating anything or computing any eigenvectors. You just run your model with the approach I showed you, your graph neural network, and this graph neural network will learn to produce positional encodings, which are nonlinear functions of eigenvectors.
I see, I see. Essentially, I'm trying to understand where the performance gains are coming, and I'm wondering whether essentially using the Laplacian itself is more than a hindrance in getting better performance or not. And,
So that's a good point. So the performance, I think, is coming from the fact that you allow your model to learn from the data, and you don't somehow impose a specific bias to the data. So it's a completely generic architecture. And the second thing is that the model has the right biases and the right complexity to be trained with the right amount of graph data.
Thank you. Great talk.
Awesome. Thank you so much.
You will see it there. You have a clock down there as well.
Okay. Is this working? Ish.
Try again.
Maybe when that one's broken.
Okay. What do you want to do?
I want to read the notes.
Then you need to mirror the Super. So next speaker is Yiwen Yuan. She's a machine learning engineer at Kumo AI. And she will talk about GNNs for recommender systems and how to go beyond this classical two-tower architecture into something that is much more expressive and much more performant. Let's see.
Thank you.
Awesome.
Hello, everyone. My name is Yiwen. I'm a software engineer at Kumo AI. Today, my presentation is about Context GNN. Context GNN is the secret sauce at Kumo. It is a novel architecture for recommendation tasks on billion-scale data that is highly efficient and has state-of-the-art performance. Today, Context GNN is used to send recommendations to over 200 million end users. It has proven to be successful to customers across industries, such as food delivery, fashion, and marketing. So today, I'll go through a quick deep dive of the secret formula of Context GNN. So Context GNN operates on structured data, which consists of interconnected tabular data. And this data can be visualized as graph. So I guess you guys have already had two presentations in the morning. So basically, the tables are nodes in the graph, and they're connected by edges defined by primary keys and foreign keys. So deep learning has proven its value for visual data and natural languages. So graph neural networks brings the revolution of deep learning to structured data. So GNN solves the link prediction problem for recommendation. Now consider this graph where it shows like an e-commerce example. So in this graph, we have different users, different actions, and different items. So each of them is a different node type. So we want to send recommendations to the users so our platform can generate more revenue. So to formulate this as a recommendation task that GNNs can solve, we can say we want to predict the set of items that the user will interact with in the next 7 days. So before I jump into the architecture of Context GNN, I want to talk about how challenging recommendation problems are in various aspects. First, the problem is temporal. So as you can see, the user behavior can vary on different days over a period of time. So for example, users can add to cart on this day and then like a product on the second day or whatever. So For a temporal problem, we need to be able to capture the user's change of behavior. For example, the user can change their location. They can also change their appetite, or they can suddenly lose interest in something. Second, the user interactions are multi-behavioral. So in the e-commerce scenario, there's multiple ways that users can interact with an item. For example, they can like an item, they can save for later, they can click on it simply, they can share with friends or whatever. So basically, we need to be able to navigate through this multi-behavioral pattern. And finally, we're really looking at large-scale data where there could be over 200 million users and 10 million items. So if we want to calculate the pairwise score for each user and item pair, then we're really looking at quadrillion pairs. So it is obvious that calculating all pairs would be super inefficient and extremely expensive. So we need to have an efficient solution here. The take-home message is that the recommendation tasks need to capture temporal changes from complicated interactions of users in a large-scale data setting. Okay, another problem that we want to tackle here is handle unseen items or items with slight modifications. So here are some examples of the use cases in our customers that we have seen. For example, in an online secondhand marketplace, we can have the same item, but the items can have different customizations and different conditions. So as you can see, there's 2 t-shirts with the same pattern, but one's for boy, one's for girl, and they're in different condition. One is brand new and the other is used. Or we could have a completely one-of-a-kind customized t-shirt where it's like an unseen, we've never seen it before in the training set. And another example is my favorite here. Actually, we worked with a meal kit delivery company where we recommend brand new recipes every week to customers. However, the recipes would only have small modifications to previous recipes. So for example, here are 3 dishes. One is a beef taco, another is a beef taco with chips, and the other is beef taco with vegetables. So these items, they have different names, different IDs, but they have really similar features. They're all made out of beef and tacos. So the problem is that we need to be able to learn learn from the similar items as well. So the take-home message from this slide is that the recommendation problem needs, recommendation system needs to make good predictions on new items through learning from the feature space. So as we mentioned previously, an entire relational database is a graph. So we split the graph into multiple smaller subgraphs where each graph captures the temporal interaction in a fixed period of time. So here's the first subgraph where we consider all actions happening on timestamp I. And here is another subgraph where we consider all the actions happening on timestamp J. So we can see there are the same user can appear in different subgraphs. So for example, in this slide, this lady has added this t-shirt to her cart at both timestamp I and timestamp J. So this is the type of the repeated behavior that the recommendation system needs to capture. On the other hand, there's also exploratory behaviors. So for example, as we can see in the subgraphs, this lady has never interacted with the sunglass or the purse. So the question here is, should we recommend those 2 items to her? Would she be potentially interested in them? So the take-home message from this slide is that the recommendation model needs to have good performance on mixed behaviors of the users. So now let's consider how existing architectures handles recommendations. So here is the 2-tower model. It is a very popular model in making recommendations used by many companies. For folks who are not familiar with the 2-tower recommendation models, let me explain briefly. So basically, we learn 2 embeddings. One is the shallow user embedding, and the other is the shallow item embeddings. And we take the dot product of these 2 embeddings, and then we calculate the logits using softmax, and then rank based off the logits. So this type of architecture has some limitations. So first of all, the item representation does not capture the user's views on the items. Second, having 2 independent representation does not capture the repeated patterns. So in summary, the two-tower model does not make a distinction between the representation of repeated purchases versus exploratory purchases. Therefore, we need a way to contextualize the predictions. Another architecture for recommendation system is pairwise recommendations. So pairwise recommendations learns a pairwise function edge for each pair of user and item. So the learned representation can capture behavioral patterns, but it's super inefficient on large-scale data set. As we mentioned previously, if we have a large-scale data for like a big company, then we're really looking at like quadratic level of complexity. So in practice, data scientists usually, what they do is to only calculate the pairwise recommendations on a smaller side via candidate generation procedure. However, the problem with that is that the effectiveness of the model is now bounded by the recall of the candidate generation procedure. However, with context GNN, we can get rid of the set of candidate generation. So now consider a hybrid approach that context GNN takes. It captures the best of both worlds. So let's take a look at the graph on the figure on the right. So we use a pairwise representation for items that the users has past interactions with. And then we use a two-tower representation for exploratory items that the users don't have interactions with. Then we fuse the two representations into to produce a single ranking across the different items. So now let's dig deep into the different part of each, the different part of the two architecture and how it's being done in context GNN. So the pairwise part is handled by GNN here, and the formulation is as follows. First, we sample a k-hop subgraph around a user, and then we add an indicator embedding to each user V. So this indicator embedding is actually inspired by IDGNN proposed by Jia Xuan. And then after that, we apply the GNN on the subgraph. Finally, we read out the user and item representation for all the items only within this subgraph. So just think of it as we sample a set of users and a set of items they interacted with, and we only do like the pairwise calculation on this set with on all the users and items within this set. Now let's take a look at the two-tower model part in context GNN. So here we actually reuse the user representation from the pairwise part. So the user embedding is taken from the GNN part, calculated from the last step. And then we query a shallow embedding matrix for the item representations. So if the data is large, then we only query a subset of the items. So we found that shallow item representation is quite effective to capture the signals while allowing us to scale to a large data or a large corpus of negative samples. Okay, now let's put the two models together to iterate. GNNs are trained on subgraphs. For each subgraph, we have items. We only sample items for users where they have interacted with this item in the past. For these items, we calculate the score using the GNN embeddings. And for the rest of the items that are not in the subgraph, we use the shallow embeddings for the item and the GNN embeddings from the pairwise model. So as you can see, there's one thing called the fusion score here, which I haven't explained in the previous slides. So the fusion score is a user-specific score. So this score is learned through an MLP to weigh the item representation of the two models. So for each item, we have like a GNN embedding, and then we also have like a shallow embedding. We use the fusion score to combine those two embeddings into one. So this score is to capture the user's personality. So for example, if the user is like more exploratory, they like to try new things, then this score will, with this score, we will learn that and then weigh the shallow embeddings more. However, up to now, our model still cannot handle the co-star items yet due to the nature of shallow item embeddings. So let's take a look at this table on the right. So we have 4 items here, and each item is stored in a more heterogeneous tabular format where we have the image, the color, which is categorical, price, which is numerical, name, which is text. So we have these 4 items here. The first 3 items, we've already seen them, users interacted with them. And we have a new product now, which is this pair of socks for kids. So since it's a new item, so no customer has ever interacted with the item, but no worry, we can still calculate the embeddings from the feature encoder and include it in the logic calculation. So the feature encoder is usually a tabular deep learning model, and at Kumo we use PyTorch Frame, which is also developed by me and my coworkers. So with this design, we can now even recommend completely cold star items to users. Okay, so that's all about it for the architecture of Context GNN. Now let's take a look at the performance of Context GNN. So the first is a Kaggle challenge. It's H&M Personalized Fashion Recommendations Challenge. In this challenge, where you need to make personalized fashion recommendation. So the score for the metric we care about for this challenge is the MAP at 12. So the contestants need to make the top 12 items, or recommend the top 12 items for each user. And in total, there's 100K items and millions of users. So Context GNN actually ranked top 1% using image data. And the good thing about Context GNN is that there's no need for any feature engineering. So basically, you load the data into Context GNN, and it'll produce the predictions. It's a lot more practical than a lot of Kaggle solutions where it takes they construct over 200 extra features and it takes 9 hours to run. So another result I'd like to present is Context GNN on Railbench. So there's already a talk about Railbench by Rishabh in the morning. So Railbench, for those who missed that, Railbench is a benchmark released by Stanford and Kumo, and it contains data sets for evaluating machine learning over relational databases. So it has been accepted to NeurIPS datasets and benchmark track this year. So Context GNN actually achieved the best performance on all recommendation tasks in Railbench. So you can see that I made a comparison of percentage boost from the best performing two-tower model and the best performing pairwise model. So as you can see, it has huge boost with respect to both of models. It means that the Context GNN has combined the good parts of the 2 types of models. We'll be releasing the paper of the Context GNN and open sourcing the code very soon, so stay tuned. And finally, I want to go over a customer success story we have. So we have a customer which is a food delivery app, and it sends notifications to users on try something new. So briefly explain what's try something new. So users order from different restaurants, and we'd like to recommend them some new restaurants to see if they'll be interested that they have never ordered from. And we're looking at over 200 million end users here. So Context GNN competes with their internal solution, and here's the result of the A/B test. So we have 30% improvement on MAP score at 10, and we have increased over 100 million revenue to the customer, and while saving them 4 million infra cost. So every day we run a batch prediction, and that finishes in 4 hours, and we send it to the customer, and they show our recommendations in their app. So last, I'd like to express my appreciation and gratitude for my team at Kumo. I think I really enjoy working on this project, and it's really the collaborative effort of the entire team. And without any one of you, Context GNN would not have been as it is today. And thank you. I'll leave some time for questions.
Thank you. Great job. Any questions? Yes. Vasilis.
Thank you very much. It was very interesting presentation and I think very inspirational work. I think this model seems to have a very good advantage in these cases. Did you consider using kind of, instead of using a combined model, using two models that can be, for example, addressing the two separate scenarios separately? You have like a router that in some cases will select in the cold start one model, or in the other cases it will select the other model.
I wouldn't call it like two models, but there's like two parts, right? You first have the GNN embeddings of the items, and you also have the shallow embeddings of the items. So you train them together, and you just decide which, for each item, which embedding you'll choose from, considering the subgraph. So I wouldn't call it like two models.
Okay, thank you. There is an intelligent router on the top trained end-to-end, right?
Yeah.
In one way to think of it.
Good. Thank you so much.
Yeah, good question.
So I have a very I'm not an expert in this area, but like recently I read an article about deep and wide deep learning network, right? So I think that addressed that problem of two-tower model. So how do you compare your approach with the deep and wide network? Is it similar results, or is there any comparison you guys have done?
Not sure what's deep and wide network, so maybe you're
I mean, deep and wide are even older than the two-tower architectures, right? The way they did it is they had, I think, kind of a dense set of features where they have a deep part of the network and a set of sparse features, which is the wide part of the network. I think the difference here is no features, and this idea, right, that basically the embedding of the items changes when you condition on the user, right? And the two-tower models, they would first, let's say, compute the embeddings of the items, and then they compute the embedding of the user and query. But in this approach, the embedding of the items changes based on who the user is. And that's why you get this additional expressive power. And then because for every user you cannot have a completely separate embedding space, you are basically having this two separate approaches and a neural network on top that kind of intelligently decide how to combine the two. Okay. Yeah. Okay. Thanks a lot. Let's finish here, do a quick coffee break, and be back for the next session of exciting talks in half an hour. Thank you.
There's so much to say.
Hello. So the next speaker is Janai Rosen. He's a PhD student at Stanford, so working with Europe, and he's doing some really transformative work. Today he will talk about building foundation models for the AI virtual cell. So Janai, the floor is yours.
Thank you so much for the introduction, Hari Laos. Hello, everyone. My name is Zinai. I'm a fourth-year PhD student in Yuri's lab, and I'm really excited to tell you about how we think a virtual cell can be built using artificial intelligence. One of the long-standing dreams of computational biology, if not the core dream of computational biology, is to be able to perform experiments in silico, so to simulate experiments. And the reason we have to do this is because cells are tremendously complex. So it's infeasible to perform wet lab experiments for all the different conditions and combinations of conditions and combinations of those combinations in the wet lab. And ideally, you want to be able to just simulate those much faster, much cheaper, and at a much larger scale on compute. So if we can move that large-scale experimentation to compute, we can use that for our large-scale data generation, and we can select only the best and most likely to succeed hypothesis to test in the wet lab for validation. However, it turns out that this is actually very difficult. So modeling biology has many different difficulties that we have to deal with when creating these models. Those difficulties include the fact that biology occurs across many different physical scales. There's many different nonlinear interactions. It's highly stochastic, and data that we generate is very noisy. That data can be generated in many different ways, but each one of those pictures of a cell or of a gene or of a tissue that we generate is going to be incomplete in some different way. So how do we approach this? Are we completely lost? Turns out that we think that using artificial intelligence and machine learning methods solves a lot of these issues, especially when we design it in a specific way. And the specific way is that we want to create a connected framework of different AI models, so foundation models or frontier scale models, that are going to simulate these increasingly complex and dynamic biological systems. How are we going to build this framework? So we can think about biology by breaking it down into three abstractions of different physical scales. So what are those physical scales? Well, the first is the molecular scale. What molecules do exist in biology that are important? Well, we have proteins, different RNA molecules, we have DNA as a whole, and we have a bunch of other kinds of molecules that are a little bit harder to model with machine learning, such as lipids or different metabolites. The next scale we have is the cellular scale. So we can think of a cell actually as a bag or a collection or a set of those molecules from the previous scale. A cell can have a certain type, like an immune cell or a neuron or a stomach cell. It can also more broadly have a state, like a cell that's dividing, or an age cell. It had some state in the past, and in the future, it's going to have some sort of different state. And the final layer of abstraction is thinking about multiple collections of cells. And so that can be cells within a tissue, and so we know that cells form these structures that span on the scale of micrometers to entire meters, or millions or trillions of cells in your entire body. And as a reference point, the human body on average has around 37 trillion cells. In addition to highly structured data sets, highly structured tissues, we also have collections of cells that are important to model from a machine learning perspective where we don't have any kind of physical connection between them. So that would be something like a blood sample where it's a disassociated set of cells. And those are also very valuable. We can, for example, predict disease state or age from those samples. How do we translate these abstractions or scales into AI or machine learning models? So for each one of these resolutions, what we're going to do is we're going to design machine learning architectures that are scalable both in their capacity to model different data and in the number of parameters, with a specific small set of inductive biases related to the biological features we're modeling, and importantly then we'll connect all those models together. So for the molecular scale, we already know that we can represent DNA, RNA, and protein individually using language modeling approaches, where the language modeling approach here is going to be to represent them as a character, or as a string of characters, where that string of characters for a protein, for example, would be a string of amino acids. And then we can perform mass language modeling, or in even some cases, causal language modeling. For the cellular scale, we can represent cells, which I'll get into more a little bit later on. We can represent them again as collections or sets of molecules, and we also have many powerful machine learning models that represent sets. And then finally, very relevant to this venue, we can represent tissues or multicellular state as graphs, where we have cells as our nodes and their physical proximity to their neighbors within the actual tissue that they're sampled from represented as edges. And so our cells are going to be nodes, their neighbors are going to be connected by edges. And then what's the key motif here, the key innovation here on this work is how we actually connect all these models together in order to maximize their training data. So when we look at our cellular-based models, we say that a cell is a collection of molecules, and we use the representations that we learned from the molecules in our cell representation. And then we perform the same motif again when we look at tissues or collections of cells. What is a cell? It's its representation from the previous physical scale, the cellular scale. What is that cell? It's a collection of molecules from the molecular scale. So you can think about this kind of, if you're familiar with word embeddings, how they're used in natural language. In word embeddings, we use those for large language models as our tokenization scheme. It's a similar approach here, except in biology, our equivalent of word embeddings have much more information within them and have much more relevant properties that we can encode than a single word. Once we learn to create these representations of these different biological entities, or these embeddings, we can interact with them in a number of different ways. And so we can interrogate them using what we call virtual instruments, which should correspond to their real world equivalents in the wet lab, or different kinds of experiments that we can run in the wet lab. So we identified two key ways that we can interact with embeddings. And the first is to manipulate embeddings. And so this is really important when we start to talk about different kinds of dynamic biological functions. So how does a cell differentiate over its lifetime? How does it respond to a perturbation? We can actually abstract away the notion of the real biological entity we're modeling here and just think about it as an embedding, and then a change in that embedding space from one starting embedding space to another to a final embedding point is going to represent the dynamic system we're modeling. So as an example of that, like I said, is we can model a cell as a starting location in the cell embedding space, apply a drug to it, and then the result is the new embedding space of the cell after it's perturbed. The next virtual instrument, or the second virtual instrument, is a virtual instrument that actually gives us useful biological information or biologically interpretable information about these embeddings. So rather than just looking at a 1,000-dimensional vector, we want to be able to decode out meaningful biological properties from these representations. An example of a meaningful biological property would be, for example, looking at the embedding of a protein and decoding its three-dimensional structure of the atoms that make up that protein as a real value. Here's another way of viewing these representation spaces. So in this visualization, which is two-dimensional, but keep in mind that these representation spaces are actually many thousands of dimensions. And this is specifically for a cell representation space. We can see how useful this is when we create this abstraction looking at the embedding spaces. So when we collect new data, we can map new data to the space. I think you can see the mouse. And we can use existing points within this embedding space as references, for example, for finding similar cell types or identifying similar disease states. We can also see within this embedding space that we can view dynamics as just changes or paths within the embedding space. So if we look at a cell as it changes over the course of aging, for example, or as a disease progresses, we can see that as a movement along a path in the embedding space itself. And then finally, you can see how we actually simulate really discrete perturbations to cell systems. For example, if you were to take a drug or apply a drug to a system as just changes from one starting cell state to a final cell state, where cell state is the result of the perturbation. And it's important to remember also, these representation spaces exist for all three of the physical scales. So that includes the molecular scale as well as the multicellular scale, and these different kinds of abstractions of going from embedding to new embedding or embedding to biological readout exist at all three of these levels, and that finally these levels are directly connected within each other through that motif of the tokenization scheme, which means that if we have any kind of interpretability system or any kind of system that does simulation based off of those or collect any information related to these different scales, it's all encoded and that information is accessible within these representations. As a very first step towards recognizing or creating the stream, we did actually create models following this framework, and the first model that we created was for the cellular scale, and we called it the universal cell embedding, also abbreviated as UCE. And so I want to tell you about how we go about designing these specific models with specific sets of biological inductive biases. And then I'm also going to tell you about how we're working on improving this model. And so This model is available open source on GitHub, and the preprint is out right now, and it's currently in the second round of reviews. So in order to represent a cell, we first need to understand how cells operate, and then what the data that we're going to use to represent the cell, how that data is measured. So every cell in your body has the exact same genetic code, or DNA. So if all the cells have the same genes, or DNA, how do they carry out such diverse functions? Why does a neuron have a different function? Why does it appear differently than a skin cell or a cell in your eye? The answer is that even though they have the exact same core set of instructions, so the same set of genes, they're going to express those genes at different levels. And what that means is that each cell is going to read off different parts of its genome into RNA molecules, which are then converted again into protein molecules at different abundances. So within each cell, we have a different quantity of each gene. And that value is called the gene expression value. And we have a really cool technology that's fairly new in the biology space, came out around 10 to 15 years ago, called single-cell RNA sequencing, that's going to actually measure those RNA molecules themselves, and we can easily relate them back to the genes that they came from, and that gives us our gene expression value. So this is going to be, for each cell, we're going to have a vector of about 20,000 dimensions, and we're going to have count values for it. Okay, so we have this data for these cells. How do we create representations for it that are informative? Why do we actually have to create low-dimensional representations? Why can't we use this data? So we have this 20,000 dimensional gene expression vector, and it turns out, unfortunately, it's highly noisy in a number of different ways. So in biology, we call these different values or these different effects batch effects. And we have a number of different ones specific to single-cell RNA sequencing data. So the first one is zero inflation. So that means although we're profiling the expression of around 20,000 genes, many of those genes are going to have zero values. So our data is highly sparse. And then even for the genes where we don't have zero values, the same gene in the exact same cell profiled in different experiments is going to have very variable expression just because of the technical noise that's added to it by these experiments. So previous solutions have solved this by trying to do various methods for dimensionality reduction, including linear methods like PCA, or slightly more complicated nonlinear PCA using variational autoencoders. The problem is because of the noise and these different batch effects within these data sets, this has been really restricting the field of single-cell RNA sequencing analysis to this kind of small data setup, right? How do we move from small data, analyzing individual data sets collected from single labs or single grad students at one time, to analyzing all the different data sets that we've collected across every experiment? In order to do that, maybe we can think about different approaches to modeling this data rather than just looking at the gene expression vector. So one solution that we could do is we could try and model cells as a sentence, which if you ask a biologist won't make any sense to them, but maybe to a machine learning crowd it does make sense, because if we can model cells as sentences, then we can apply some sort of framework for natural language, such as causal decoding to them, and we have a new nice way of representing cells. However, if we're going to do that, we have to be really careful, and we have to think back to our biological inductive biases before we just apply these new architectures. So if we're going to create a cell, if we're going to represent a cell as a sentence, how are you going to order the genes of that cell in that sentence? And the first way that we might think about doing this is by just randomly ordering the genes or using some sort of fixed alphabetical ordering. However, this is not going to add any information to the model itself, and gene names actually themselves turn out to not be informative. The second way is that we can actually just sort the expression vector, so order genes by their expression within that cell. However, this also has some pretty poor inductive biases. So given that we have count data, we have to decide how we break ties, which happens a lot with single-cell data. Additionally, if we think about the inductive bias we're adding to the model, we're assigning really high importance to the most highly expressed genes in the cell, but it turns out, unfortunately, most of the highly expressed genes in cells are not really informative for determining how the unique function of that cell. Okay, so if we can't represent a cell as a sentence, how can we represent it? Well, we can just represent it as a bag or a set, and so that just means a collection of items without any specific ordering for it. We're still able to use transformer architectures here because transformers actually naturally don't have any ordering to them, right? If we just don't add positional encodings, then it works very well as a method for encoding sets. So now the way that we model the cell is going to be basically exactly reminiscent of the way that the cell itself is measured in the wet lab, which is in the wet lab, we take a sample of the RNA molecules in the cell, and now we're going to represent that cell again as a sample of those same molecules. The final question here is, how do we connect this back to the molecular scale? Right? We're working at the cellular scale, but in this virtual cell framework, we want to connect to their previous scale at the lower level of resolution. So if a cell is a bag of genes, what is a gene then? One way that we could represent a gene is by using methods that are kind of similar to word2vec, which is maybe how different word embedding models originally worked, which is based off of co-expression data, which is from different kinds of experiments, but it turns out a lot of those are very redundant. And additionally, it'd be really hard to personalize that to an individual's human genetic variation, since these are just single representations of reference genes. The second, which is really interesting work that came from another lab at Stanford, is by using large language models to summarize literature or summarize reference pages for different genes, reference web pages for different genes to create embeddings of them. However, again, this falls into the same difficulties where maybe we can't model species that are poorly studied or different genes that are poorly studied, and it could also be difficult to translate this approach to individual human genetic variation. So the solution that we settled on was to actually just represent genes by their real genetic sequence, specifically their protein coding sequence. Then a final consideration for UCE is that we want the space to be universal, which means that if we collect similar cells in different experiments, everyone should be able to map those cells to the same space, to the same locations in embedding space. That location embedding space should represent real similarity between cells. So this is very different from the approach in single cell that's typically been done, which is either just to not map different data sets together and only analyze single data sets at a time, or to train models from scratch every time you collect new data, especially training those models from scratch with some sort of implicit bias about cell type locations or cell type populations within those data sets, which negatively affects the model. So all those model choices combine to inform us on how we design the UC architecture. So we're going to represent a cell as a sample of the genes that it expressed, weighted by those genes' expression in the cell and with replacement. We're going to represent those genes, so tokenizing them, using a large protein language model called the ESM2 language model. That's our equivalent of word embeddings here. And we're going to take that representation and feed it as an input to a transformer model, which is going to create an embedding of the cell as a whole. And that transformer model specifically is a 33-layer, 650 million parameter transformer model. We trained UCE on 36 million cells from more than 350 different data sets, dozens of tissues, and importantly, 8 different species. And because of those different model design choices, we can map new data sets to the exact same space as UCE. So what I'm showing here is dimensionality reduction UMAP plots of the 1,280 dimensional UCE space, where each point in that plot is a cell, and they're colored by the author's cell types. And so you see that the embedding space recaptures the structure related to cell type information, even though that's not passed into the model directly. And what I haven't shown on this slide yet actually is these are from 4 different species that weren't in the training data at all, and because we've connected the molecular scale to the cellular scale, the model has this implicit understanding of any genes from any species that we throw at it. Although this is currently just showing for different species, it's also important to understand how we can extrapolate this approach to human genetic variation. So even though we have the same set of genes between different people, essentially, it's the small differences in those genes that makes each one of us who we are. So I want to skip ahead a few slides due to time restraints, and I want to tell you about how we're working on improving this model. So I think you might have heard about this project earlier in the day, but we really want to improve how we model the molecular scale first and form a strong basis or a strong base for our future models on the cellular scale and the multicellular scale. And so we're doing that by creating new representations of all the different molecules that are available for us to model and measure at the molecular scale. And if we look at how UCE fits into this right now with UCE, we have a cellular scale model that represents genes as proteins. And what we want is a new model that can represent all the different biomolecules available to us. And we called that model, as you might have heard earlier, the dogma language model. Awesome. I think it's time for questions. I'd like to thank all my collaborators and obviously my PI as well, Yuri. Thanks, everyone.
Do you have any questions? So, if not, let's thank Yanai again. So the next speaker is Min-Kai Su. He will talk about diffusion models, if I'm not mistaken, for tabular data. No, generative AI for synthetic data.
Yeah. Hello, everyone. I'm Min-Kai. I'm a PhD student at Stanford, working with Professor Leskovich. Today, I'm going to talk about our recent work on generative model, especially diffusion model for your synthetic data generation. So first thing is, what is synthetic data? So we already have the database which contains all your data. So synthetic data it's an artificial copy of your real data. So the copy means our synthetic data should really be similar to your real data, but the artificial means it should be different, still different from your real data, because we need to preserve all the privacy in your private data. Why we need synthetic data? First thing is, in this large language model era, so we have all kinds of machine learning model, either a prediction model we have talked about today, and we also have some retrieval augmented generation model. All the model need extensive data to deal with, either train the model or as a database to retrieve the knowledge. So we always need more data. But second thing is, the data is always privacy, and in many cases, it is even regulated, like finance, healthcare, and real estate. So in all these cases, we need synthetic data. So actually, there is already some solution for this problem, and actually, it is even more commercial. So there is generative adversarial nets, which is many years ago. Like we have a generator which can generate some data. We have another discriminator to discriminate whether the data is real or not. And the generator aims to beat the discriminator. Then we can have a good generator, which can generate pretty good data. And then people also use it for your tabular data generation. But people also realize the data has many drawbacks, like pretty bad controllability, and also the model sometimes just memorize your data. So we'll still leak your privacy. Here, what we deal with this problem is by diffusion model. So diffusion model is pretty advanced model where the generation process is, we always start from a very noisy structure, and then we run our model to progressively denoise the data until we generate a good data. And one thing I want to highlight here is, actually, diffusion model is the cool technology behind many entertainment tools you see from OpenAI, like DALL-E or Sora, which generate a cool image or cool video. Yeah, but in our work, we unleash the full power of a diffusion model, but for tabular data generation. Here we show a cool example of our generation dynamics, where we start from the random initial table. Like this table is for movie information generation. We predefine the column of the movie, like budget, duration, rating language, and so on. So many rich features. And we run the diffusion model. Again, I run the visualization again. So we can progressively denoise all the feature until we generate a good data for you. Here is our framework. We call our model TapeDiff. And the technical challenge is different from image, where every pixel is just some continuous value, and different from your longer model, where each token is just a word, which is discrete representation. Here, tabular data is very complicated and highly multimodal. There, you will have text information, you will have some continuous information, some integer, like your age or whatever, and also have some many categorical features. We need to develop such a multimodal model to cover all your features all at once. So here is our model. So we begin from your clean data, and we will define a diffusion process where we do some cool diffusion process to destroy both your categorical data and your continuous data. And we novelly learn a model. The model is a transformer where we input the noise data, it will output a clean version of the data. So when we do generation, we just begin from a very initial, very noisy tabular and repeatedly put into our model, and eventually we can recover a very good, very clean data for your downstream tasks. We do some comprehensive evaluation on our model. Here are 3 aspects of our model. First thing is statistical properties. So when we really want to use the synthetic data, when it is useful, it always needs to capture the underlying signal in your original data. So we do all kinds of evaluation on the distribution of a continuous feature, discrete feature, and we later show that our model can really capture all the signal in your data set. Second thing is, even we can capture the signal for each individual feature. Another thing is, in tabular data, what we want to generate is entry by entry. We still need the entry to capture the correlation. Like maybe a good movie is with some fiction, like a favor, or some movie will have a bad favor. We need to capture the correlation in each entry. So second thing is, we also study the correlation in our synthetic data and your real data. And we compare the correlation and see we really recover all the signal in the data set. Important thing is still privacy. So we can always generate good data, but what if our data is just an exact copy of your data? This will still make your data have some leak issue. So finally, we also have some privacy privacy evaluation. Okay, yeah. Let me introduce all the evaluation step by step. So first thing is we plot all the distribution of your real data and of the data generated by different methods. And as shown in the first row of our figure here, we can perfectly recover the continuous distribution for your numerical features. And the last row is about your categorical feature, and also show here our table-diff model now beat all GAN-based model and also other relevant diffusion-based model, and we achieve the state-of-the-art for capturing the statistical properties of your tabular data. Second thing, we also show the some correlation between our generated data and the real data. The correlation within each entry, within each rows, between different features, and we compare with the correlation captured by our data and your real data. So in short, the figure is rendered by like a lower or lighter color indicate a better property. And I think the figure is pretty intuitive and straightforward, and very significant. Our method is much better than all the baseline model. So last thing is, we also need our synthetic data to preserve your data privacy. What we do here is, given your real data, we train our model on your real data, and we generate a same size of your real data. Then we will use another discriminator model to try to classify these two sets of data, and we see whether this classification loss can really, whether they can detect the real data or not. Then, as shown in this metric, our model also achieved the best score, where the detector or the discriminator cannot detect any synthetic data at all, which means they cannot be classified, and yeah, it preserves your privacy. Yeah, last thing, I'm going to talk about some cool application of our model. First thing is machine learning efficiency. So, we always want to generate synthetic data. So after generation, we always need to use it. So machine learning efficiency is, we will train the model on your data and generate the new data, and we train your ChargeBoost model, either regression model or classification model, on our data. And then we will test the performance on the real data, on the real test set. So if the test score is pretty good, which means our generated data already be useful for your downstream machine learning tasks. Yeah, so here is the score. After training on our data and all the baseline models, we can show that our model can always achieve the best score, which means our generated data is really in high quality. So here I want to highlight several. I think this is one of the most important metric you will care about because people really want to use the machine learning efficiency of the generated data. So here I highlight some baseline here. So CT-GAN is the original GAN model I introduced before, which is the GAN-based model for synthetic data generation, and TVAE and Google, not really Google. So these two methods are VAE-based model, and other models on the bottom of the figure are other diffusion-based model. So they are all very relevant and advanced model, and we show that our method actually beat all the model, considering different data set, like adult, shopper, magic, Beijing, all this kind of tabular data. Next cool application I want to highlight is missing data imputation. So this is some ability coming from the nature of a diffusion model. So here I first show a cool figure which is the computer vision task of diffusion model. So which is usually called imprinting. Like we always have some image, we can destroy partial information of the image, and as we can see, diffusion model nowadays can always recover the true information of the image there. So recover a good face or good background, or yeah, a very cute animal. So, but this is also something very relevant in your database problems. So when we have a database, many features are missing, and actually our diffusion model can also just be freely translated into this imputation task. We can just treat the table on the front as the initial state. So we already introduced our model run like a denosing process for the whole table. So we can always just take the missing table as our initial state, and we will still run our denosing process to recover the data. But the good thing is we can manually design which part to recover, which part to always take to keep fixed. So in this imputation setting, we can just keep all the information we already know, keep them fixed during the whole sampling process, and then we will just gradually recover the missing data. And finally, we can show, yeah, our model can do this cool imputation task. Yes, and for this task, we specifically also do experiment and have some numerical result here. As shown in the table, again, we beat the advanced model from some company, TipSyn, and we achieve the best result. So last part, I think I will talk about some future work in my mind. So first thing is, I think most of the companies thinking about retrieval augmented generation, which is called RAG system now. So, but actually RAG system always have this privacy issue. Like when you really want to create some useful data, you maybe always need some very private data. Yeah, maybe like a client, for a client agent, you will provide the information from other chats with other customers. But actually those customers ask some very, very private data, private information, and you just want the RAG system to follow the philosophy here, but you don't want them to really follow all the data details already revealed here. So yeah, so here we create our solution. So if a customer is chatting with this RAG system, they can first retrieve from the database and retrieve a specific tabular data for this data, and then we can quickly fine-tune a model, or even not fine-tune, or even our model already trained on the data. We can just take this retrieval data as conditioning and generate a new artificial copy of the data, and then all the chat is just conditioned on or retrieved on our generated data instead of our real data and preserve your privacy. And this is some very direct usage, and I want to say, I think a tabular diffusion model has a potential for a very powerful tabular foundation model. So as a foundation model, it will provide many, many possibilities of your tabular data. So given a table, you can automatically add rows because we can generate new data. You can add some new columns because we can do missing value imputation. So you can do some very magic like augmentation of your table in both dimensions. And most importantly, as shown in some in computer vision and also in NLP task, another useful thing is this generative model learning is always a pre-training objective. And actually, our model, if you put your raw into the model, we can get a very informative embedding. And you know, embedding is the key of your retrieval augmented generation system. So our vision here is, in the future, you will have your large language model as agent. You will have your database as retrieval augmented generation database. But you know, all the agent is many agents are talking about tool using or whatever. So current RAG system will call so many different tools to retrieve from the data, do some cleaning of the data, summarize the data, and finally give some generation to the user. But here, our vision is we hope TableDiff eventually can be a foundation model where it's the foundational tool between your database and your agent system. Whenever the customer asks a question, the large language model agent can just use our TableDiff model to either create a new model or impute missing data, or just want to protect the data and make an artificial copy of your data. And most importantly, we can also embed the question and find a good solution in your database. The model now is released on, it's not released, but I already have a GitHub on it, but we are still cleaning the code, which will come out very soon. Our core developer team is by some cool students from USC, Stanford, and also Professor Stefan Urman and Professor Yuri Leskovich. Yeah, that's all. Thank you.
Thank you, Min-Kai. So very cool work. Do we have any questions? Here.
Great presentation. How do you train your discriminator in that? Is that like done with synthetic data, or it feels like it could be like a loop in how you train your discriminator?
Discriminator on, you mean GAN model?
Yeah, like to detect whether it's synthetic or real data.
Oh, I think that is from some package. So
okay.
I guess it's just a charge boost. Yeah.
Okay, thank you.
Another question over there.
Is it 1, 2, 3? Okay. So my question is, looking at this from a perspective of anonymization, so I was thinking that maybe we can think of data anonymization as some sort of very specific way of doing generative AI, right? So in some sense, by taking all this data and then generating, I was thinking, is there any way that this can be applied more generally for anonymizing data while keeping very, very close to the true distribution of the data? But not just generating, but more specifically anonymizing, if this makes sense.
I think I didn't fully get the question.
So my question is whether this technology can be used for anonymizing the data, not necessarily viewing it as generating new data, but anonymizing existing data sets. I'm not sure if this makes sense. Maybe we can discuss it later.
Oh, you mean unmemorizing the data?
Anonymizing data. So you have, let's say, a medical data set and you want to hide some information before using it, but of course hiding information may degrade the quality. So instead of hiding, let's say, information, maybe using such technique to, in some way, anonymize the data while keeping as close to.
Oh, I see. I think I would say the current model is just make the data into some fake data. Like for your sensitive information, it will just generate some other information there, but it's not anonymized. Yeah, I guess it needs to combine with large language model to specifically tell which part is sensitive. Yeah.
Okay. Yeah, that would be interesting. Okay, thank you.
So let's thank Minkai again. And the last speaker for today's workshop will be Swapnil Bemte from, I hope I didn't kill it, so from Hitachi America. And the talk is about learning production functions for supply chains with graph neural networks.
So, good afternoon, everyone. Thank you for joining. Myself, Swapnil Bemde, researcher at Hitachi America. Today, I'll be presenting our work on learning production function for supply chain using graph neural networks. This is a collaboration between Stanford and Hitachi. So, before diving in, I would like to share a bit about our unique collaboration. This research is collaboration between Stanford's Professor Urey's lab and Hitachi America. So, and also supported by Stanford Data Science Affiliates program. So, I mean, to give an introduction about supply chain, what is supply chain? So, supply chain is a $1 trillion valued network where fluctuations in demand and shortages are propagated and amplified through the multi-tier structure. When one supplier faces any shortage, the impact propagates to their customer and beyond, so potentially affecting the entire industry. Understanding and managing these complex interaction is crucial for maintaining stability and resilience in today's interconnected economy. So just to give one example of supply chain disruption, so here you see different tiers of automobile. So on the left, there are like a deep tier, which when a supplier is making some wafers and facing any shortages in wafers, it could potentially lead delays in automobile part makers. And essentially, these delays will be reflected in automakers' production. So such disruptions amplify as they move up the chain, leading to widespread production delays and potential billion-dollar losses. So a recent example from the 3-day strike happened on the US East Coast, significantly affected the trade. So these ports were covering about 34% of automobile trade. And it is projected that even though strike lasted only for 3 days, it is projected that it affects the production in automobiles up to 3 to 4 weeks. So this shows the strong need for a model that captures disruptions across multi-tier supply chains, allowing us better to predict and manage the risks. So in this research, we tackle some challenges. First is hidden production functions. So many internal transformations within firms are unobserved, meaning we often don't know which specific inputs are being used for which specific outputs. Understanding these internal dependencies is critical to identify bottlenecks in the network. So another challenge is lack of transparency. Most of the suppliers do not know beyond their adjacent suppliers or buyers. And the third is data completeness. Due to sensitivity and privacy of the transaction, some of the data is missing, and the capturing supply chain dynamics is challenging in such case. So moving to the supply chain network and its propagations. An important fact of supply chain is that each firm often produces multiple products, which creates complex dependencies. So in this figure, we see various inputs like silicon, rubber, and copper wires flowing through unobserved production functions. And these inputs are transformed into different outputs, batteries, and GPUs. The challenge here is understanding these hidden processes as they affect how the shortages and delays in the input will propagate and impact output products. So talking about the supply chain network, the data we have acquired includes thousands of firms across the globe with transactions from last 5 years. We represent these transactions as a heterogeneous graph with both firm nodes and product nodes. Then these transactions are represented as time-stamped hyperedges, where each edge include a supplier node, a buyer node, and product node. So these hyperedges represent another challenge for our model, since most existing temporal GNNs are developed for edges between two nodes. So our goal, we have mainly two goals. First is we want to learn the production functions within supply chain. This means identifying how specific inputs are transformed into output within the firms. For example, knowing the exact combination of wafers, copper wires, and other components required to produce GPUs or batteries. And our second goal is to predict future transactions. By analyzing past transaction data and production dependencies, we aim to forecast which firms will interact and what products will be traded in the future. So this prediction is very essential for proactive inventory management or early risk detection. And finally, the model we build has to support hyperedges as well. So to tackle these challenges and the objectives, supply chain introduces a new type of temporal graph, which we call temporal production graphs. The existing graphs are not sufficient to capture the complexities because they lack the production-specific transformation that happen over the time within the firms. So the TPGs address this by using temporal graphs governed by production functions, which essentially map how inputs are converted to outputs. This enables us to make a precise prediction about how input shortages like specific raw materials might impact production outputs. And the existing GNNs are not designed to handle these kinds of temporal production dependencies. So we developed a specialized GNN architecture tailored for temporal production graphs. We propose a method that integrates temporal GNN with a novel inventory module tailored for TPGs. The temporal GNN uses recurrent update from the past transactions to capture changing dependencies, helping us to learn internal production function. The inventory module tracks the product inflows and outflows, uses attention weights to model dependencies. Moving to the model in more detail, the basic idea of our model is that we combine any generic temporal GNN with a novel inventory module. This allows us to jointly infer production functions and predict future transactions. So firstly, every node in our model has a memory, which is a vector capturing current state. And when a transaction occurs, we update the memories of the supplier node, buyer node, and the product node. And this is our way to support hyper edges, since all three nodes are updated. Then we construct node embeddings using a neighborhood aggregation over memories. This can be any sort of GNN, such as simple aggregation or attention-based. Then we predict future links by concatenating the embeddings and passing through an MLP decoder. To tell more about inventory module explicitly, so these inventory modules represent many products that each firm has in storage. The key is that the past transaction also update the inventory for each firm. So when firm buys a product, we add those products to the inventory. When a firm sells the product, we need to subtract from the inventory what the firm internally consumed in order to produce those products. So this is what the internal production function comes in, since we need to map from external production to internal consumption. In order to learn these production functions, we use the product embeddings and learn attention weights between the products. So basic idea is a product attends to its parts. For example, a battery attends to copper wires. So this allows, and finally we use the inventory as input to link prediction. This allows inventory to both react to past transactions and future transactions. For example, if a firm is low on an input product that they commonly need, they can put an order to receive the future transaction of that input. So this is so we also created supply chain simulator. So the need for supply chain simulator is we also have real world data. So missing transactions, missing production functions, incomplete records, logistic constraints were the main limitations for the real world data. To test and train our model, we developed a supply sim simulation tool that mimics a complex and multi-tier supply chain. And it recreates the realistic supply chain structure with like characteristic like power law, degree distribution, community structure, low clustering, and time varying transactions. Supply sim also allows us conduct some scenario analysis by simulating multiple variants, like considering supply chain shocks and missing transactions. Additionally, by providing this synthetic data that closely resembles actual supply chain dynamics, helps for advancing supply chain research. So moving to experiments, our experiments focus on two goals or two objectives. Firstly, learning production function, and another is predicting future edges. So here, the experiments, the results for learning production functions is how well our model can learn production function, which we tested on like synthetic data as well as real world data. So we used three baselines. First is random baseline, other is temporal correlations, point-wise mutual information, and node-to-weight embeddings. So these baselines capture different aspects of input-output relationships. And in this table, you can see we see the mean average precision across different settings. The inventory module, particularly the version using embeddings, consistently outperforms all the baselines. On real-world data, particularly IED, which is an industrial equipment data set that we have created, our model achieved a notable improvement over the baseline. So these results highlight the effectiveness of our inventory-based approach in accurately learning production functions. So to give more detail, here on the left, you can see true production functions from like synthetic data. On the right, you can see the inventory module learned production functions. So try to mimic the true production functions here. Another objective that we wanted to work on was predicting future edges and improve the prediction accuracy. So our experiment on predicting future edges aimed to evaluate models' accuracy in forecasting the existence of the future transactions. So this task was evaluated using MRR, which is mean reciprocal rank, where higher MRR indicates better performance. We compared our model, so SCTGN and SC graph mixer, which is a temporal graph network, and graph mixer, which are popular temporal GNNs, with and without inventory modules, against several baselines like edge bank, static, and graph transformers. As shown in the table, SCTGN with inventory consistently outperforms other models across multiple data sets. So overall, these findings shows that the effectiveness of our approach for future transaction prediction in complex supply chain. So just to give an idea about how we can use these results for and its applications. So our model has significant real-world applications. Like first, by learning production functions, we enhance visibility within the supply chain, allowing firms to better understand their product processes, identify bottlenecks, and improve operational efficiency. And secondly, forecasting future transactions supports critical tasks such as demand forecasting, early risk detection, and inventory optimization. One cool application I would like to show in terms of visualization is that on the right there is a end product, which is a battery pack, and as you go down there are there are different raw materials you can see, where you can see that the contribution of a different raw material with respect to the final product. At last, our model has proved to be robust under real-world challenges, performing well even with supply chain shocks, missing data, which demonstrates its practical applicability. Looking ahead, we plan to extend our method to other domains, such as biological networks and organizational structures, and integrate causal inferences techniques. Additionally, we would like to include more data sources to further improve prediction accuracy. And at last, I would like to thank all the collaborators, especially Serena, who is the first author of this paper, a recent PhD graduate and incoming professor at UC Berkeley. Yeah. Thank you.
Any questions for the speaker?
I actually have a question. So you mentioned hyperedges, which are like two nodes with a node in the middle. Have you tried just using regular nodes and then treating the node features of the middle one as like an edge attribute?
So we also have two types of nodes. So first is firm node and other is product node.
Yeah.
So What are you suggesting exactly? I mean,
Well, okay, it's like you have source node, destination node, and something in between for hyperedge, right? There's
yes,
3 nodes,
product,
right?
Yes, yeah.
And so in traditional GNNs, you just have source and destination, but you can have an attribute for the edge.
Yes, yes.
That's generally like in PyG, it's dot edge attribute. Have you tried that approach, and do you know if there's like any trade-offs you've experienced, or?
So we also make use of some other attributes. So we have information about the cost for every transaction, and also like what is the port for the start and the end. So we make use of these attributes for defining any transaction.
I'm just going at a higher level of basically like those are node features or
Yeah.
some sort of feature for the edge.
Edge feature. Yes.
Yeah, so for the edge features, could you just concatenate the middle node's features to those and treat the middle node as just another feature of the edge? Okay. Do you see what I'm saying?
We can talk later. Yeah, I think so. Yeah.
Another question over there?
So my question is that I'm assuming the number of suppliers and the producers, the buyers and suppliers and the number of products are changing every day, right? So when you build this temporal graph model, how do you solve the node and edge changing problem, especially for like the newcomers or the co-start nodes or links?
Yes, I mean, that's a really good question, actually. So, yeah, I mean, definitely so we were, one of the real world data set we have, over 5 years of data. So between that few timestamps, definitely a lot of buyers change their suppliers and supply chain constantly change. So we found that through experiments that the TGN model, temporal graph network, actually kind of tracks such kind of dependencies because it has some time dimensional embeddings as well. So through experiments we found that, and also for inventory, I think it's we use those embeddings from the learned temporal GNNs to infer production functions.
Okay, thank you.
So let's thank the speaker again.
Yes. Thank you.
And next we have our poster slam session.
Here? Yeah, I believe so. Should be. Make it. It just kicked you out, so just. That should be it.
So let's start with the first speaker.
Good evening, everyone. It's my pleasure to present our work on transform model for hypergraph here at this workshop. Transform model have been successful in NLP and computer vision, and they have been extended for graph structured data resulting in graph transformer that have shown amazing performance in molecular graph, social network, etc. However, the problem is graph transformer can only capture direct relation that present in a network. However, the network may contain some higher order complex structure that they may fail to capture. So to address this problem here, we present a topology guided hypergraph transformer that can capture and model a higher order relation between entities even present in a simple graph. Unlike traditional unlike traditional hypergraph transform model that use traditional attention network to discover important node and hyperedges, semantically important node and hyperedges, here we present TSTN that can detect and model important node and hyperedges from both semantic and structure perspective. So here, first we construct a hypergraph from graph depends on the nodes higher order structural relation within the network. And then we introduce two core components. The first one is node feature enrichment via structural and spatial encoding, where we introduce 4 different encoders to capture local and global structural knowledge along with spatial information of node that we integrate with the initial node representation to enrich its representation. And the second module is structure our attention, which here we introduce 2 different measures to discover structurally important nodes for a hyperedge and structurally important hyperedges for a node, and thus enhance the overall representation for the downstream task. If you feel interested, you are welcome to the poster session. Thank you very much.
Hi, everyone. My name is Roman. I am from the chemical engineering department here at Stanford, here to present work on accelerating the generation of molecular conformations with latent diffusion models. So you probably haven't missed that this year's Nobel Prize in chemistry went to AI. It's fair to say that predicting structure of biomolecules has been a game changer in the field. However, protein structures, smart biologists told me that protein structures are fake news, because what we really care about is the dynamics, right, of the molecule. At the nanoscale, these things keep on moving with Brownian motion, and it really is those dynamics that we need to capture to understand the properties of molecules. So an intriguing approach here is to sample a lot of conformations so we can then understand how that distribution looks like in general to capture those dynamics. But then we get bottlenecked by the speed at which we can generate molecules. So my poster here presents work that we did to try to accelerate the generation of molecular conformations using equivariant GNNs and latent diffusion models. Long story short, we can accelerate up to 8 times with the same quality of molecular conformations. And if you're ready to open up, to have a trade-off with quality, we can get up to 16x or 30x with very limited loss of quality. Come see us. I'd love to answer any questions about how we could apply this. So thank you very much.
Hi everyone, I'm Mustafa Hajij. Today I'm going to talk about our new package, TopoX. So TopoX is a collection of packages that generalize deep learning to topological spaces. So TopoX consists of 3 packages, TopoNetX, TopoEmbedX, and TopoModelX. So we tried, so the purpose for this package is to democratize and start creating packages for deep learning on topological spaces. So we went to the most popular libraries in deep learning that creates, that basically allow you to create models on graphs. So TopoNetX generalize Network X, which is a library to create graphs with SciPy and NumPy backends. TopoEmbedX basically allows you to do topological representation learning, basically generalization for Node2Vec. So this is a library that's sister to Karate Club, if you're familiar with this library. And TopoModelX is a library that basically allows you to create topological neural networks on topological spaces. So by topological spaces, here I mean hypergraphs, simplicial complexes, set complexes, and combinatorial complexes. So our library is unit tested, and there is a lot of tutorials that allow you to start right away. And we have a lot of start creating a lot of interest in the community. Thank you so much.
Hi, my name is Michael.
I will be presenting the work on one single foundational model. You can claim it like that for node classification on any graph. So basically, what I wanted to say is that the days where you had to train a single GNN for every data set and do node classification on each train, the days are over. You don't have to do it, guys, anymore. So now we have one model, one single pre-trained model that can work for node classification on absolutely any graph. Any number of classes, any features, number of features, any density, any kind of graph graphs you can imagine. We can run zero-shot inference on those graphs better than GC and GAT, other baselines that you would train from scratch. If you're interested in how this magic works, check out my poster.
Hi everyone, this is Xiangsong from Amazon, and I'm going to present the Graphstone all-in-one graph machine learning framework for industrial applications. This is an open source framework we developed upon Deep Graph library, and it's designed fully for the enterprise use cases. So the design principle for this framework is to simplify the use case. We expect, so for every user, you're starting from a tabular data, like in Packet format or CSV format, and you can use just 2 or 3 command line commands to run a GNN training on large scales, even with billions of edges. The biggest graph we run using this framework is 100 billion edges, and we have practiced it in a lot of internal Amazon graphs. So I'm happy to talk with you in the poster session. Thank you.
Hello, so I'm Francisco Vilas-Cruz Navarro. I'm a research scientist at the Flatiron Institute. Yeah, it was supposed to be a movie, it doesn't matter. So, I'm a cosmologist. Our goal is basically to understand what are the goals, what are the laws and the constituents of the universe. So, unfortunately, yeah, this is a complex problem. We only have like one universe. So what we do is basically to create universe. You know, when my mother asked me, what do I do? So this is what I do. I create universes. And, you know, in these universes, what you do is to change a little bit the laws and the constituents of the universe. So you will have basically like different galaxy catalogs. And the idea is that, you know, we are using now a geometric deep learning for the first time in this field to basically try to extract the information, the fundamental physics of these catalogs. So if you are interested in, you know, how this works, come to my poster. Also, the other thing is that, you know, this data set, this is the largest collection of numerical simulations ever run. We have spent really like tens of millions of CPU hours. This is a very beautiful data set, and, you know, it's public available. So I'm pretty sure this will be also of interest for many of you. Thank you.
Hello, everyone. My name is Sean. I'm from NVIDIA Deep Learning Framework team. Today, I'm very excited to present our recent work integrating rapid whole graph feature and graph store into PyG remote backends APIs. So this integration accelerates and scales GNN data loading process significantly by minimizing the CPU overhead during sampling, as well as supporting customized feature graph partitioning and simple 1D graph sharding over multiple machines. And this feature and graph store API is framework agnostic, which means it will just consume data, PyG or DGL data sets and transfer it back to whole graph managed storage. And then we will provide API to transfer the sample output into PyG compatible format. So that means that users just need to focus on their own customized or optimized data loading pipeline or downstream GNN tasks. Let Rapid library to worry about efficient GPU-accelerated feature and graph store access across multiple machines. If you are interested in our work, please come talk to us in the poster session. Thank you.
Hello all, good afternoon. It's my pleasure to be here and present my poster on software performance characterization. My name is Ronaldo Canizales. I'm studying my PhD in Colorado State University. As a motivational example, even tiny changes in source code can lead to significant performance differences, and this is particularly true in heterogeneous architectures. So our framework uses graph machine learning to, from any given source code, make predictions on performance metrics. And in this pipeline, we address 3 specific challenges by designing an old code-to-graph representation based on equality saturation to make it more expressive, augmenting a graph-level embedding method to make it faster, and building our own custom heterogeneous dataset with more than 150 million of instances. And yeah, for more details in our methodology and results, please feel free to visit my poster.
Hi, everyone. So our work aims to address some of the systems challenges that are currently existing with a lot of RAG approaches that try to incorporate structured knowledge bases. So whenever we try to use these knowledge graphs and documents and retrieve them from the same space, right? We have a dual task of traversing through this knowledge graph and then retrieving documents from it, which causes some end-to-end retrieval overhead. So our project aims to reduce this end-to-end retrieval latency.
So our approach tries to tackle this problem by utilizing 2 different types of cache architectures. One of which is we try to, for a given node that we extract from a knowledge graph based on a query, we try to cache the relevant documents that are retrieved when processing that node. And we also try an approach where instead of doing an exact match to the node when we're taking in new queries, we try to find a semantic match that already exists in the cache. And we explore what the accuracy versus latency reduction trade-off is when we approach these 2 different caching mechanisms. But yeah, if you guys are interested in learning more about our work, feel free to come and approach us in our poster. Thank you.
Hi everyone, my name is Carolina Gonzalez. I'm a PhD student at the Scripps Research Institute in San Diego, and today I'm presenting Drug-Based Reasoning Explainer. This is a model that provides interpretable explanations for drug repositioning. So in this work, we're really interested in providing new uses for already existing drugs using a biomedical knowledge graph. And for this, we use a case-based reasoning strategy where we first retrieve similar drug entities, and by reusing the reasoning patterns of these similar drug entities, we are able to find novel connections. The most important part of our project is that we are not only able to find these novel connections, but also provide the biological mechanisms that explain these connections. We also integrate an explainable module that identify which of these connections are more important for our model. And I think that's it. If you're interested on drug repositioning and knowledge graphs and biomedical knowledge graphs, come talk to me during the poster session.
Hi everyone, my name is Brian Shi. I'm from engineering at Neo4j. At Neo4j, we work on graph databases, graph algorithms, and GNNs. Our poster will be on GraphRag with GNN plus LLM on Neo4j. So we'll first present a general architecture for the problem. The architecture itself contains 2 main components. So given the natural language question that is in essence a multi-hop graph question, we first perform knowledge graph retrieval that returns a subgraph. The retrieval system itself contains multiple steps. The question and the subgraph context are then fed into a GNN plus LLM system, which is optimized jointly. We'll provide a specific implementation for the architecture, and then we'll do a case study on a stock prime dataset hosted in Neo4j with the GNN plus LLM box implemented with GRetriever. We'll show our results beats the best baseline in the benchmark considerably, and actually in the poster we'll have a small variation which pushes the metrics even higher. We'll show intermediate metrics as well as analyzing the role that each component plays in the whole process. And finally, we'll present some engineering bottlenecks as well as research directions. We're open for collaboration at Neo4j, and see you at the poster. Thank you very much.
Hi, I'm Anish. I'm a postdoc at Memorial Sloan Kettering Cancer Center in New York. One of the problems in oncology is that you often don't have tens of thousands or hundreds of thousands or even millions of samples that you see in other disciplines. What do you do if you only have 50 samples or 500 samples? And so here we present work where we use Olivier-Ricci curvature, which is a measure of robustness on a graph, to take data from a specific cancer type here, which is multiple myeloma, and from that we extract unique information and try to find novel therapeutic targets. And so in this, at the poster, I'll show you how we took, using this graph measure, how we took data from the bone marrow and found a gene that we think could help people who have relapsed with multiple myeloma. So if you're interested, please swing by. Thank you.
Hello everyone, my name is Injin Ling, a PhD student from Purdue University. I'm here to present a joint work with Microsoft, rethinking node representation interpretation through relation coherence. So a typical node representation interpretation process will be like this one. We will have a graph, and it will encode various node relation or graph signal in the graph. And there will be a GNN, like graph-based model like GNN, try to learn like those node representation. So there will be another interpretation method, try to understand like what's encoded in those embedding space, for example, and then you will output the interpretation score like the table on the right-hand side. It's showing like the relation, how this embedding space encodes various kinds of node relation. If the score is higher, that means that you have a strong relation between these node relations. And previous approach usually focused on interpretation, and we found out, we proposed an interpretation method in the evaluation process and found that previous interpretation method usually have very low interpretation accuracy. So as a result, we proposed another interpretation framework. And if you are interested in how our evaluation process look like and how our interpretation method look like, please stop by our poster session. Thank you.
Hello everyone, my name is Yorgos Tsitsikas. I'm a recent PhD graduate from UC Riverside, and I'd like to talk a little bit about our work Multigraph Explorer. So this work was created from the need to create more sophisticated ways of analyzing unsupervised clustering. The problem with clustering is that human in the loop is really, really important. So essentially what we're doing with this, I'm sorry, I forgot to change the slide. We try to, first of all, study multigraphs, where many tools give tools mostly for simple graphs, but also what we're doing different is we are allowing people who design new methods to very efficiently visualize all the results and also the intermediate hyperparameter tuning so that we can have an efficient human in the loop and increase the iterations, the speed of iterations. If you're interested to learn more about it, please find me in the poster session.
Hello, everyone. I am Maria. I work in responsible AI at LinkedIn, and I'm presenting my master's thesis research. Well, the future wireless networks are going to be very complicated. Somebody looking up Dr. Leskovich on LinkedIn and a wireless, an autonomous vehicle on the road will both be on a wireless network, and they will both require widely different reliability, user service rate, throughput, and latency. A reinforcement learning agent on a wireless network can assign network resources to each user category based on their need. But to train such a reinforcement learning agent is quite challenging. So my work here basically tells that if you use the graphical representation of the wireless network such that it encapsulates the topological and geographical information of the wireless network along with its parameters and its current state. Then such a reinforcement learning agent trains with 15% less episodes, but it is able to automate the assigning of the network resources in the same manner as trained through a tabular, trained with a tabular representation of wireless network. So keeping the topological and geographical information of the wireless network can train such a reinforcement learning agent faster. For further details, let's meet at the poster. Thank you.
Hi everyone, my name is Moritz Rietschel. I come from the architecture department at UC Berkeley. I'm going to talk about some work on graphs and CAD, so 3D modeling. There's actually a very common approach in 3D modeling for the real world, like architecture or engineering, that uses graphs to model a 3D model. So imagine, for example, a point in space and something like a diameter as input nodes that we then connect to a circle node to create a circle, and then connect that circle node to an extrusion node. So in this way, we can model a flow graph logic of a 3D model. And the work that I'm presenting at my poster, oh, it's a bit small, is actually creating such geometric logic nodes using an LLM. So we can have an input like an umbrella and come up with this structure that is actually a geometric modeling graph of an umbrella to fulfill this. So what the user gets back is a parametric model of an umbrella that is actually displayed as a graph, so the user can then work on that graph or edit the graph. And I'm excited to integrate more graph-specific learning at all layers, and I'm excited to talk to you about this at my poster. Thank you.
Hello everyone, my name is Vijay and I'm a new postdoc at Stanford. I'll be presenting graph transformers for large graphs. This work is a scalable graph transformer framework that can be used to efficiently handle large graphs with millions of nodes. We try to design the framework with the combination of local and global graph information while addressing their respective limitations, such as the neighborhood explosion in the local modules, as well as the quadratic complexity in the global module. So we try to address that and put it in a large graph transformer framework. The local module has a new tokenization strategy that can be used to have a larger receptive field with cheaper operations, such as 2-hop for a 4-hop receptive field, and a global module which uses an approximate codebook-based attention to compute global representations. Combining both of these, we have the update algorithms which tries to avoid the training complexity with respect to the number of nodes in the graph, which allows it to scale over very large graphs. We use this to scale the model for graph representation learning on graphs with up to 100 million nodes. For further details, you can scan the QR and let's have a chat during the poster session. Thank you so much.
Hi, I'm Yezi. I'm from University of California, Irvine. So in this research, we studied the fairness problem in link prediction from a data-centric perspective. Our solution is to learn a fairness-enhanced graph from the input graph such that a link predictor trained on it can generate fair link prediction even if it does not have fairness design. So if you're interested, please come over to my poster sessions. That's all. Thank you.
Good. So this was the end of the poster slam. This kind of is the end of the program on the stage. What follows is the happy hour, some little food outside, and the poster session here in the main room, as well as I think outside in the corridor. Thank you everyone for attending, and Again, thank you, Joseph, Malvana, Lata, Sarah, Jason, and the rest of the team for a great organization. Thank you again.